So focus more on week 5, week 6 content. And I think Piyush sir has done revision of week 5, week 6 last day. Today I will at first start with week 7, sorry, week 8 revision. We will discuss some important topics because week 8 is the next important week. So we'll do that, and maybe after that we can have a complete kind of discussion, doubt discussion session where we will discuss any doubt that you might have. Week 7, I will not discuss in detail, or let's say, so to say, not at all, basically, because that's some theoretical points, and that's upon you. Just have a see, look at a few questions from previous year, or let's say, look at your practice question. That also is fine. At most, one theoretical question might come, and one psycho PG connection question might come from week 7. So just prepare that. As long as you have your practice questions solved, and graded questions obviously you have to give, and maybe you have a just look around the slides of week 7, I hope it should be fine. Don't have to go into great depths for week 7. Okay, so let me just start with week 8, but before that let me have a open uh, question to all of you. So please ask your doubts, okay? And if someone wants to, let's ask many doubts, keep your hand raised. So everyone who wants to ask something, that I have doubt in this part or that part, right? Any week 7, 8, 5, 6, any week, general topic wise, any doubt you have, okay? Raise your hand, and I will ask one by one. You can tell the doubt so that I can keep a note of it. Then maybe discuss at the end of the session. Yeah, just keep your hands raised. Let me share my screen. Yeah, Sudhir, go ahead.
Sir, could you please explain once this dependency preserving concept while breaking the table? So I have doubt in that.
Okay, dependency preservation. Yeah, go ahead. Whoever has doubt, huh? Tell one by one.
Yeah, actually, sir, show the decomposition if it is not in any normal form. How to make the decomposition after
Not in
finding it
any,
is.
it's not even in the second normal form you want to say, the initial state.
Yeah, yes, yes.
Okay, let's say,
Sir, fourth normal form.
okay.
BCNF also, sir.
Okay. So as expected, most of the doubts will be there from week 5 and 6, and that's how it should be anyways. So nice.
Yes, yes.
And sir, वो disk capacity question was.
Sorry, which question?
And वो disk capacity or platers, sectors, tracks.
In a week.
Hard disk, hard disk. That I will discuss. That I will discuss. Anyways, I'm not writing that because that I will anyway discuss. Yeah. Anything else? I don't think anything else is anyway there. So, chalo, let's start. If someone has any doubt, they can ask in between. No problem. And please don't raise your hand, as I won't be able to see that. Again, I'm repeating. Just interrupt me in between and ask.
Elenco,
Sir,
please ask.
MVD.
That I have written. 4NF is basically your MVD. So,
Okay, okay.
yeah. Well, fine. So let me start week 8 discussion first. It won't take much time, I hope. Then maybe I will come back to week 5, 6. These three, four
Yes, sir.
topics. Yeah. Uh, how should we do it? So okay, let me just first I will not go sequential. Let me discuss the numericals which are more important for week 8 concepts. So at first I will discuss the hard disk part, and then we will, let's say, go to solve some numericals. One or two numerical is enough to discuss all the concepts, and then we will just go through the slides of week 8 and see if there is something to discuss. Week 8 again, binary search tree creation and this hard disk numerical, and one to theoretical question might come from your memory storage, right? So which storage is volatile, which is non-volatile, which has more, let's say, cost per unit, stuff like that might come from week 8 also. Or two theoretical question on storage medium. One binary search tree creation question might come, that is important, how to make a binary search tree. And another is your this hard disk access question might come. These are the important parts.
Sir, one doubt regarding the theory question you mentioned, like cost per unit decreases as we go down, right? The
Down means
from RAM to secondary memory, tertiary memory, like that, it will decrease.
uh,
What about throughput?
throughput also decreases.
Oh, okay. What exactly is that meaning? Throughput.
Throughput, the term throughput. Okay, so let me see. The term, somehow my cursor is not working properly today. Anyway, so the term, just a second, okay. Okay, so the term throughput basically means your number of jobs done per second. So number of jobs done by time taken. So now this is a general term. Now, as you can see, in case of your memory devices, the word, I mean, the throughput term refers to the number of jobs. In this case, is basically number of data transfer. So that can be mostly read or write. So in any number of read write operations done divided by the time taken for the read write operation, or basically you can also say the number of access, disk access or device access. So because read write operation is the way to access the device, so I can just group both read and write operation together and say that that basically means one device access. So the number of device access, successful device access, that can be handled in a given amount per unit time, right? So that is basically your throughput. So as you go, I mean, from primary memory towards the secondary memory, towards your hard disk and these other devices, what happens is your speed of the, let's say, the speed with which these devices can operate decreases. So your RAM can, let's say, cater to 10 reads or 10 writes in 1 millisecond of time, whereas in order to do 10 reads on a hard disk, from a hard disk, or 10 write on a hard disk, it will take you around, let's say, maybe 1 second or 1.5 second or 2 seconds, something like that. But RAM can do that in 10 milliseconds of time. So because of that, RAM is much faster. So as you go down this hierarchy, obviously speed the speed with which you can access the device decreases, and that's why, since the speed decreases, you can understand that the number of jobs done, that also will decrease with time. So therefore the throughput will also decrease. So RAM has the highest throughput.
Okay,
I
sir.
mean, not RAM, actually cache memory has the highest throughput, but yeah, so
Yeah,
basically,
okay,
yeah.
got it.
Okay. So we were going to discuss.
Well,
Someone,
sir,
huh?
registers would be the highest, right?
Yes, sir. I have also.
Sorry, what?
What about registers?
Registers will be highest. I mean, I'm not
Mm-hmm.
going into that whole hierarchy. That yeah, registers
Mm-hmm.
will be highest. After that, your L1 cache, then L2, L3 cache. I mean, I don't know whether L1, L2 caches are discussed in these lectures, but anyways, so L1 cache, L2 cache, L3 cache is there. Then you will have other units of memory in between hierarchy. So yeah, basically that's the as you go down the ladder, the throughput decreases. That's the idea. Okay, so regarding the hard disk, okay, so or magnetic disk, so just something not that important for tomorrow. I mean, this quiz too, but just generally asking. So, do you know, by the way, how all the storage mediums separately stores memory? I mean, how do they basically store a data? Let's say a hard disk, right? So, hard disk, how does a traditional hard disk stores memory? I mean, not memory, stores data. Sorry, can someone tell that?
So it's 0 and 1.
That is fine. That any electronic device you take, that is basically storing 0 and 1. But how it stores, that makes the primary difference between the storage devices. So is
You mean to ask about data structures or?
no, not the data structure. When you are storing data in a hard disk, it's about hardware storage or physical storage. Data structure comes much after that in the hierarchy. Data structures will only work when you have an operating system to read through that data structure, or at least a firmware to read through that data structure, right? So yeah, so that comes much later. What I'm asking is more about how the physical storage is done on a magnetic hard disk.
Magnetic, it is north and south pole is there. So they are differentiating between the north and south 0 and 1 like that. I hope so.
Nice. Yeah, that's more toward the answer I want. So okay. So basically, hard disk stores memory by using magnetism. That's why we call it magnetic hard disk or magnetic tape. So how it does that is it might not be that important for your exams or anything, but just for knowledge purpose, I'm saying. So once you have the hard disk, right? So the disk inside the hard disk or HDD device, they have a upper coating, which is a magnetic material. Without not going into that much detail, so it's a you can say it's a magnetic material, and there is a read write head that we talked about and that we are going to solve numericals on. That read write head is basically another magnetic device. So this magnetic device will in case I want to write a 1 on the hard disk at some point, this magnetic device will create one polar structure. I mean, there are two poles, as our friend already said, north south pole. So it will have one particular pole oriented dipole. That will be one in one particular orientation, which will be, let's say, the north orientation that reflects 1, or otherwise the south orientation that reflects 0. Okay, so things are a little bit trickier than that, but we are not going into that much detail. But you can just say that to differentiate between these two, 1 and 0, we have this let's say polarity differences or orientation differences of the dipole, and that read write head basically goes through that magnetic material which is present on top of the hard disk, and it HS 1 or 0 depending upon, I mean, HS the 1 and 0 value by having these different notions of oriented moments, the magnetic moments. And yeah, so that basically, if you have a strong electromagnetic field present I mean, near your hard disk, or let's say I have a, so in many this science fiction movie, not also science fiction, in normal non-fiction movies as well, you might have seen these devices which are called electromagnetic pulse generator or EMP devices. I mean, it's not like that EMPs, it doesn't work like the way they are shown in movies, at least. But the idea is correct. If somehow you have a strong EMP wave coming near any magnetic storage device, it will wipe out your entire data. A real example, non-fiction real example, would be a solar storm. So when you have a very, very strong solar storm, it might completely destroy Earth's magnetic field, and that's why it might also destroy any, let's say, technical devices, electronic devices which works upon magnetism. Okay, so solar storm is one real example. If a very strong solar storm occurs someday, then it might completely wipe out all magnetic devices and data that we have stored on Earth. So that's the important point, and that is the reason nowadays later on we came up with other storage technology. So if you see now the SDD, which is your solid state drive, which many of us use to make our booting faster and normal operations of our computer faster. So those store the data in a completely different manner. It doesn't use any magnetism. It stores, basically it uses semiconductor technology, right? Your flash drive also uses semiconductor technology, but SSD uses semiconductor technology in a completely different manner. That's another new discussion. Yeah, without going into that much detail, I just wanted to share this. So since we are anyway learning hard disk, it's better to know a little bit trivia about that. Okay, so uh, okay, coming back to our topic. So basically, in case of your disk access time numericals, there are 3 points that you have to take care. First of all, your seek time. So what is seek time? So I hope that all of you are now comfortable with the hard disk structure. So how basically a hard disk looks is,
Does the time take to exact right position of?
yeah, I'm coming to that. So the basically the hard disk structure is you will have this kind of concentric.
Please ask the question. Don't raise the hand. There's no hand.
Yeah, if someone wants to ask something, go ahead and ask. Okay, I won't be able to see if someone is asking something. So don't raise hand. So we have this, sorry for the drawing, but we have this kind of concentric circles, right? And let's say this is one track, right? Then this is another track. Likewise, obviously in all the platters I will have tracks, and let us say if I draw it like this, I mean an imaginary line, a dot 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 I am giving. So obviously you can understand that this will kind of look like an imaginary cylinder, right? It's not a cylinder, it's not connected, nothing is there. But let's say this particular track will have a corresponding track over here as well. I mean, which is in the same line, vertical line, right? So this track, I mean, so let's say this track and then so this so assume again this one will also have a corresponding track over here, because these are concentric kind of situations. So these are called cylinders. Many of us have this doubt that where is the cylinder that we are talking about. Yeah, so each of this is a cylinder. Okay, so all the concentric tracks that we have, when I consider the whole platter as, I mean whole set of platters, then each track inside each platter is a part of that corresponding cylinder. I mean, that's cylinder is imaginary. There is no physical cylinder. Okay, so this kind of looks like a cylinder when I consider all the tracks at that particular level together. That's why we are calling it cylinder.
Here, I have a doubt here.
Yeah, yeah.
In case of this cylinder, suppose on the both the surface of the platter, there are 300 or 3000 track also, right? So is it sure that on both the surfaces, the track will be of the same radius?
Ha
On the
ha. Yeah, yeah, yeah,
yes.
yeah. Same
Okay.
radius. Same
Okay.
radius.
On the both the side, they are on the same radius, right?
They are on the same radius. Correct.
And they will be counted as two. One
Yeah.
side.
Yeah,
Okay.
they will be counted. So let us say if they ask you that, mostly they will ask you what is the capacity of a disk or something like that. So then you don't have to mix and match the concept of cylinder along with the concept of both surfaces. But yeah, you might not need to use it, but still the radius is same. To answer
There
your
was
question.
one question regarding this, the number of cylinders. So I was not sure that if suppose there are five tracks on one
There will be
surface,
five cylinders.
so on the other surface of the cylinder, are those five are going to be on the same radius or maybe on different radius? If the radius is different, then number of the cylinder is not going to be defined.
Correct, correct. That's okay. But then again, that information is anyway not given to you, right? And anyway, the radius is same, but still, if no other information is given to you, that means you have to answer on, I mean, whatever is given, right? So
Okay.
therefore, in that case, it is 5. Anyway.
Okay, sir. Okay, fine. Thanks.
So okay, so these are cylinders. So I discussed this concept of cylinder because many of us mix this up. That okay, I understood the idea of track, I understood sectors and all of that, but where are the cylinders? Cylinders are not physically present. It's basically at a particular, let's say, radius. If I'm considering the track at a particular radius for all the platters, then that constitutes the imaginary cylinder. That's how it looks like. Okay, so now that is one thing. Now what is sector? Sector is basically each of these track is divided into these portions, and each of these unit portions of data storage is called sector. So you can, so why this is done? Because you cannot read a data which is less than a sector. So whenever you are reading a data or sending a data to your, let's say from hard disk to your CPU unit, that will be at least one sector long data. Generally it is not one sector, it is much more than that, but most of the time it will be one block long data. And block is another concept. So what is a block? Block is a concept of operating system. Okay, so more about an operating system, and then we can have multiple sectors present as a part of a block. If I have in the OS, let's say I say that a block contains 4 sectors. So then that's I mean 4 sector, in if each sector is 512 bytes, so 4 into 512, that much data is there inside one block. That's another terminology, but normally speaking, one sector is the minimum unit that you can read, or writing can be done, because within a sector you might want to make a change, but reading will always happen in discrete units of sector. You cannot read half a sector and send it to the hard processor. Or
Sir,
huh,
this block, sir, in one of the question I have seen that the relation between the block and the capacity of the sector. Suppose there are capacity of the sector is some 512 MB. Then the capacity of the block should be the multiple of this.
correct,
So I
correct,
did
correct.
not get that, sir.
Yeah. So that's what I'm saying, right? So a block is basically a collection of sector. Let's say I say that one block equal to, let's say I say n sectors. This n can vary. Okay, this n can vary. There is, I mean, it can change. Now, obviously, this will be a discrete number. So as long as this is a discrete number, the capacity of one block, you can understand it will always be an integral multiple of the capacity of sector. Right? It will be some lambda times capacity of sector.
Can we say the sector is the diameter or is a portion of in the disk?
Yeah, that's what I drawn over here, right? So a sector is basically a small part, a discrete part on a track. I mean, so we will say that a track has, let's say, maybe 100 and let's say 128 sectors. So that means that track is divided into 128 sectors. So each of these unit is basically a sector. This is a sector. This is a sector. This area is a sector. Then this area is another sector, like that.
So like make a round, make a circle and just it can be divided into multiple diameter. Is it so? So the between the one diameter and next diameter is the sector. Can we assume that?
No, not between. It is on the track itself. So let's say if I, from the top view, if the track looks like this.
Yes.
Right. Let's say this is this track which I have drawn, and the inner one which is there, let's say it is inside it. Let's say it looks like this. This is the top view. Okay, and this is your the empty space in between. So anyway, so if that is the case, so each sector will, let's say this is this much to this much space of this green line is your first sector.
Okay.
Then this much to this much space of your green line is your second sector. Now you might ask that this is a line,
Hmm.
then how does it make sense to store a memory? Yeah, so basically you will be, as I said, right? So it will just etch a 0 or a 1. So that takes a very little amount of space. So that 0 1
Okay.
0 1, let's say a sequence of, so it's, let's say if I say that a sector's memory is 512 byte long, right, equal to capacity of sector, if that is the capacity of one sector, if I tell you this thing, right, in the most of the question will have this as the capacity of the sector. If that's the case, that means what? Bytes means that 8 bit, right? One byte means 8 bit of information. So 512 byte means 512 into 8 bit. So this is essentially this 512 into 8, whatever the value is, that many 0 and 1, if you arrange side by side, that
Hmm.
is basically one sector of information,
Got it, sir.
right?
And sir, then how it is related to block then?
That's what I said. The capacity of a block is some integral time capacity of sector, because one block is a logical unit. You cannot say that a block is kind of a collection of, let's say, 4 sectors over here. Let's say this is 3 and 4 sectors are there. You collected them together. So just like cylinder is a concept which is logical. It's not physically there is no cylinder. Block is also a concept which is logical. It's a group of sectors. Okay, now it's not always fixed that I can have 4 sectors in a block, or I can have 2 sectors in a block, or 8 sectors in a block. It's not always like that. Okay, so it will be some integral multiple, that's for sure. So if you any question which is asking you, will give you the information, or will ask the question in a specific manner. So let's say the capacity of the block will always be an integral multiple of sector. So if sector is 512, some multiple of that will be the capacity of the block, and which is not a multiple will cannot be the capacity of that block. So that's the idea. So block is basically some sectors grouped together. Now how many sectors grouped together is a question of the operating system.
So the block contains many blocks will be there, but all the blocks having a particular n number of sector only, not different. Like
Correct. If you have a fixed, I mean, norm to which you are sticking in a particular operating system, then that's what you have to follow. You cannot have one block having 4 sector, another one having 8 sector. No, it's not like that.
Okay.
Right? But for different OS, it can be different. For different installation, it can be different. For different environment, it can be different. There is no fixed norm that X number of sector is always present inside one block. That's not the case.
Okay.
Okay, fine. So anyway, so this is kind of the structure of our hard disk platters and all of that, and we might have multiple surface etching. So in that case, as we have already discussed, these tracks will be both on the upper side and also on the lower side over here, which is kind of inside this. I cannot draw that, but yeah, so inside you can, on the lower side of the platter as well, you will have tracks, and that will be of the same radius. So yeah. So that is basically the structure of hard disk. Now you have a read-write head attached over here, okay, with a spindle at each level, obviously. I kind of drew it in a line manner. It's not always that kind of, it's separate axis. All these spindles work separately. So anyway, so now therefore the idea of seek time and rotational latency comes over here. So what is seek time? So first of all, let us say again I am drawing this track, this outer track from a top view. So if this is my outer track, and let's say this is my inner track, okay, and let's say there is another track over here. I draw 3 tracks like this. So let's say these are the 3 tracks. Now what happens is, let's say initially my this read-write head was actually, let's say, at this point. Okay, I mean just from a top view, I cannot draw it in that manner. Just assume that it is pointing to this point. If you look from the side, it will look like this basically. So that's what I'm saying. Anyway, so if the spindle is currently, the read write head is currently at this point, and let's say I want to read the sector which is over here, right, over here, from here to here. I want to read this sector, this area. So how will I do that? First of all, I have to take my spindle and lay it on this track, right? The spindle was over here. Now I have to take it and put it over here at this point. Or let's say for ease of understanding, I want to read this part, the inner one, over here. So what we'll have to do, I will have to take this read write head and place it on top of this track, right? Now I'm not putting it on any area, I'm just taking it and carrying it in a single straight line fashion from here to here and placing it on top of this track, exactly on top of this track. So it's like taking this and placing this exactly on top of the inner track from the outer track, right? Okay, so that is the first task. So this is what we call seek time. So when you are seeking the read write head from whichever position it is to that correspond, on top of the track which you want to read, right? So that will take a time, right? That's a single dimensional movement, lengthwise or widthwise, whatever you want to call it, one directional movement, and that is the seeking time. Now once you have placed this, let's say over here on this point you have placed it, right? After that you will have to read the sector. So in order to read that particular sector, you have to rotate the disk. So now the disk platter will start rotating. So the platter will rotate and arrange itself. So this whole thing will rotate, let's say in this direction, and it will arrange, it will take this area at this point, right? So because the disk will rotate, so this area will come to just below the read write head now. Now the read write head will drop, and once it drop down on that particular area, and it will just, then again the platter will start rotating in the opposite direction, let us say in this direction, to read whatever data is present one by one in this area. So that's how it will work. So first is taking the read write head to on the top of the track, that is your seek time. Then in order to place the sector which we want to read below the read write head, we have to rotate the disk, and that is called rotational latency.
Sir, like while calculating rotational latency, should it be average rotational latency or just given thing we can add?
Average. Why? Because that's the idea. So as I said that once you place the read write head over here, you might get the next sector just after here. I mean, just after that, right? So wherever the read write head is placed, luckily, if you, I mean, you are lucky, you might have your sector might be just located over here near the read write head or over here. So in that case, you don't have to rotate at all, and that will, the rotational latency will be very, very less, kind of near zero. It will not be zero, but it will be near zero. On the other hand, if your rotational latency, I mean, if you have the sector over here, right, that is the farthest, because you have to do a 180-degree rotation, and that is the farthest rotation that you might need in order to basically go to the correct sector. So either you might have very little rotational latency, or in order to place the track, place the read write head on top of the correct sector, you might have to do a 180-degree rotation. So that is the highest, worst case rotation. So therefore, rotational latency is considered the average of your time period. Why? Because at most, since 180-degree of rotation you might have to do, so that is what, half of a complete rotation, right? So therefore, we basically calculate the total time taken for one complete rotation and half it as the average rotational latency. So you always have to consider average rotational latency.
Okay.
Right? Because rotational latency, normally speaking, rotational latency can be either very less or it can be one complete rotation time, which is basically your, let's say 3000 RPM is the disk's rotational speed. So 60 by 3000, whatever is the value, that is your rotational latency in the worst possible scenario. So therefore, we consider average rotational latency, and we take it as half of the time taken to make one complete rotation.
Yeah, okay. So that RPM means from that we will be calculating time taken for one rotation, and then we have to half it, right?
Exactly, exactly. Okay. So this is half of time period, as you can understand, rotational latency. Seek time, so in the slide you can see the average seek time concept is given. Most of the cases, the question will give you seek time and you will use it as, I mean, without making any average or anything like that, because most of the time seek time, whenever I'm giving you in the form of a seek time, I'm telling you this is the seek time, then you use that directly. I mean, you don't have to half it or anything to average it out. Because rotational latency, I will not give you. Most of the time, the question will not give you rotational latency. It will only give you this is the disk's RPM. And whenever you are calculating something, you have to calculate the rotational latency on your own. And when you are doing that, you are essentially have to apply the concept that, okay, once the rotation is done, once I have placed the retry head, I might have to do a 180-degree rotation, or I might have to just, I can get the value over there only. So therefore, there is a half of rotational latency concept coming here, half of rotation time period concept coming here. So since rotational latency is not separately given to me, therefore when I am calculating the rotational latency from the time period of one complete rotation, I have to half it down. So that is the idea of why we are doing averaging out for rotational latency. Actually, seek time is also averaged out, and the reason for that is you don't know which axis will be on which track. You might be located at the outermost track, and the next seek maybe for the just the next concentric track after that. So that will be very less, near to zero seek time. But in case the seek is to the innermost track of the disk, then you have to do a long translation, linear translation, translatory motion. You have to go so as to reach the correct track. So therefore, seek time is also averaged out. But most of the question that will come will not ask you to calculate the seek time. Like here, you are calculating the rotational latency, right? We are not giving you rotational latency. We are just telling you this is the RPM. You are calculating it, and therefore you are averaging it out. But seek time will be given to you, so you don't do half or anything over there. But suppose a question comes in the form where seek time is not directly given to you, rather you have to calculate it. Now, how do you calculate seek time? So I already told you the seek time is basically what? The time taken to take the read write head and put it on the correct track which you want to read. Not at the correct position of the sector, but on the correct track. Now, if I tell you that in a question that let us say a magnetic disk is given with so and so sector tracks and all of that, right? And the time taken, now this is how the question is given, that the time taken in order to move the read write head from one track to its nearest track is, let's say 2 milliseconds, or let's say a 0.5 milliseconds. So time taken to move read write head to the immediate track bidirectionally. I mean, outer way or inner way, it doesn't make any difference. Bidirectionally is, let's say 0.5 millisecond. Okay, and no other information is given to you, and let us say the RPM value is given and how many tracks are there, all these things are given. Now I ask you, what is the disk access time? So now in that case, the disk access time will be seek time plus rotational delay. Now rotational delay you calculated from RPM and halved it out and you got the answer. But seek time is not given here directly. I have never mentioned anywhere that this is the seek time, but I have given you this information. So if you calculate seek time from this kind of information given to you, then you have to average it out. Why? Because now you see, since you will now calculate it on your own, how will you calculate it? You don't know that. I mean, I have not given you any information regarding the next axis will be from the next track or not. I have not asked you anything regarding which axis is coming when, nothing. I have just told you that from one track to the nearest track, it takes this much time. So in this case, it is kind of the same rotational latency concept coming here. You have to basically average it out because you don't know on which track the next axis will come. So therefore, the worst case scenario can be, you can say that it is just on the nearest track, it will be 0.5 millisecond. Right? If I have to, I mean, it might so happen the next axis is just on the next track, and therefore I have to just move one track, so that is 0.5 millisecond in any direction. Or in the worst case scenario, it might come to be the farthest track, so that will be what, plus first of all I will average it out, so divide by 2. So plus how much? The worst case scenario. So what is the worst case scenario? How will I calculate it? It will be 0.5, which is the time taken to move from each track, from one track to another track, into the number of tracks. Exactly. So basically if I have 30 tracks, so 30. Okay, whatever. So n. So this will be your basically, I mean, your average seek time. Okay. So in that case, you have to calculate the average. But if I am directly giving you in the question, this is the seek time, then don't go and divide by 2 because it's there in the slide. In the slide, it is given when you are calculating the seek time. Like when you calculate rotational latency, you divide it by half, right? Sorry, divide it by 2. So that is the idea. But I have not seen any question coming which asks you this idea. But know this thing: if sometime a question come, you might have to answer. So bottom line is, when you calculate any rotational delay or seek time, then you have to do the halving. Otherwise, if it is directly given to you, don't do any divide by 2 or anything. Okay. So yeah, so those are the concept. After that, we have this access time, simple access time of a disk, which is basically your seek time plus your rotational delay or rotational latency, whatever you want to call it. And then we have disk transfer time or data transfer time, which is basically the time taken to rotate. Once you have placed yourself at the correct sector, what is the time taken to read the data that you want to, the amount of data that you want to read, data transfer time. And that is actually quite easy, which will be basically the amount of data you are reading, right? So whatever that, this many bytes. So that amount of data, so how will you calculate the data transfer time? So basically, let us say your, your disk track, right? Your track has, let's say, so track has, let's say, X sectors, right? X sectors. Now each sector is 512 byte long. We know that. So sector's capacity is 512 bytes. So therefore, one track has how much data? So track's capacity
X into 5.
Capacity is 512x. So this is the track's capacity. Now we know that a track is that one circle, right? So therefore, in one complete rotation, one track's complete data is read. So that means 512x amount of data is read in one rotation of the disk, right? So if that is the case, you know the speed. So 512x divided by your rotational speed, whatever it is. So let's say the time taken to make one complete rotation in 2 milliseconds. So that is basically 2. So
This is
how will
rate.
tell.
Sir, this is sir, this is a rate of transfer file.
Rate of transfer. That is transfer time, right? So transfer, what transfer rate actually, correct? Yeah. So time, not rate. Disk transfer rate. So this will be your rate. So this is the, your 512x amount of data is divided by your this much time. So this is basically this bytes per second or per millisecond or whatever. Now when you multiply this whole thing, right? If that is the time taken to, if that is the disk transfer data transfer rate, so that much data can be transformed in so much milliseconds of time. So from there you can easily calculate that if you have to read, let's say, 10 bytes of data, how much time will it take? So that you can calculate easily. So
one track is one round, right?
One track is one round. Yeah.
Yeah.
So yeah, so these are all the concepts, just simple. Just keep in mind that whenever we are calculating rotational latency from RPM divided by 2, whenever seek time is directly given, directly use it. If you have to calculate seek time on the basis of taking the read write head from one track to another, then you have to consider both the cases. First is just the immediate track seek time, which is the given value. Let's say I tell you one track to another track's time is zero point 0.1 millisecond. So your 0.1 millisecond plus the worst case scenario, which is 0.1 into number of tracks divided by 2, you get the average seek time. So then you can get the access time. Data transfer rate is also simple, as I just discussed. So these are the things. And then you might have a question. This is disk access is one kind of question. Another question is simple multiplication, that these many sectors are present in one track. There are so many tracks on one platter. There are so many surfaces, either one or two surfaces on a platter, right? Something like that. And then you have to multiply all of them. That's it. Or I might also ask you that how many bits are required to access, let's say, the sectors in a disk. So, for example, if I have, let's say, I ask you this question: given a magnetic disk, given a HDD or hard disk, which has, let's say, 60 tracks, okay, and let's say two surfaces, let's say 64 sectors per track, and 512 bytes of sector capacity.
What is surface?
I told now this a platter can be edged on both direction. This is on top, or let's say on the bottom side as well. I mean, over here.
Okay, the top and bottom.
Yeah. So that means two surface means on both side of the platter it is there.
Okay.
So that basically means when I say 60 tracks are there, each platter has 60 tracks. That means, right? So that in that case, if I say two surfaces, so that means actually each platter has 120 tracks. You have to do that multiplication. And let's say I tell you there are maybe 32 platters. Okay, 32 platters. Or basically platters is the correct term to use. You sometimes they might also use the word disk, but disk is not the correct term. Platter is the correct term. So 32 platters are there, and maybe let's make it a little more difficult. Okay, okay, fine, no problem. So 32, there are 32 platters. So if that is the case, then I ask you that how many bits are required? How many bits should be the address field? Right, so when I ask you address field, as I already told you, this tests one concept of one understanding, which is basically what do you, so let me just go ahead with the answer and let us see what happens. So that will be more beneficial. Okay, so how to calculate this? So
first we should calculate the total number of sectors required.
Okay, so total sectors, what will be the answer for that? I mean, just one by one tell the multiplication. Total sectors will be 60 tracks are 32 platters are there. So 32 platters
into 2 into 60
into 60 tracks. Okay.
Into 64.
To 64. Nice. So these many sectors are there. Right? After that.
And we have to find the minimum number of bits that is required to express these many sectors.
Correct. So we will not multiply 512 here?
No, we don't.
Okay, so that is the concept which is very important. Sometimes they might ask you how many bits are required to address the sector. So they ask you, then you anyway know. I mean, it's quite easy. But sometimes they might not ask you about sector or anything. They might direct ask how many bits should be there in the address field to access this basically hard disk. So then you might think, okay, address field, then this is sector, this so many sectors, into each sector is 512 byte, and we will give you the information just to confuse you, just let us say, and then you multiply this 512. No, don't do that. Address is always, as I already told, a sector is the minimum unit of information which you basically get access to and then you read from the hard disk. So whenever I am asking about address, it essentially means you are accessing a particular sector of the hard disk. So always hard disk is sector addressable memory. So each sector is each address. So therefore, don't go into multiplying each sector address by 512. Sorry, don't go into multiply 512 to basically address each byte of the hard disk. That's not how it works. So do not multiply this 512 in the address field when you are calculating address field. It will be only up to the number of sector. So if that is the total number of sector, now you basically take a log value of log base to log base to ceiling value of this whole thing, and that's your answer. Right? Okay.
So can you explain the reason why we don't multiply 512 bytes?
Because hard disk is because your HDD is sector addressable memory. So basically, when I'm asking you to get to a specific location, that will always be a sector itself. Okay, the address field will always be sector. But if the question is specifically asking you how many bits are required to address each byte of the hard disk, if it is asking you specifically about how many bits are required to address each byte of the hard disk, specifically it is mentioning each byte of the hard disk. So then you have to multiply by 512 bytes, because these many sectors into 512 bytes, that's basically the whole capacity of the hard disk. That is fine. That is a separate question. But normally, if they are asking you how many bytes, then you multiply by 512. If they are asking you how many sectors, then you don't have to multiply by 512. But if they are not giving you any information regarding byte or sector, and they are simply asking you address, they are giving this term address. So then you have to know what does this address mean. I understand when byte is given, I will multiply by 512 and get the log value. I understand when sector is asked, I will not multiply by 512 and only get up to the point of sectors, and then I will get the log value. But if I am asking you address, what shall you do? So the address is basically the sector. Whenever you are talking about address, that means you are talking about sectors. So therefore, I will not go inside each sector again and multiply by 512. Okay, so basically we are asking you how many sectors are there, because when you are writing an address of the hard disk, you basically mean how many sectors are there. You are just going into the sectors. That's it. Okay. Okay, so that is one thing. I don't think there is anything else in this hard disk part. We will see some numerical just for check. Okay, just before that, let me discuss all the concept. So that BST, binary search tree, is another important part, and the third numerical type that is there in this week is your least recently used, that flushing concept. Okay. So let us discuss that. So what is this buffer management? So you see, whenever we are basically writing a program, or I mean, whenever there is something running on in the your processor, right? Our RAM is limited, right? It's not like we have a huge RAM that can store everything. But whatever processor is working upon, it will always take the data or the required resources from RAM. It will not go into hard disk directly. Processor does not identify hard disk as well. Your processor will only be able to see what is there inside RAM. Okay, it won't be able to see what, I mean, it doesn't know anything outside the RAM. RAM knows that there is hard disk and there are all these other memory devices and all of that that I can use, that RAM knows. But for the processor's perspective, it only knows that my whole world is the RAM. There is nothing else outside RAM. Okay, so if that is the case, you can understand that the processor is the one who is asking and referencing for all the memory data and everything. So it will ask for a particular data, and that data will be fetched and given to processor. So if that is the case, that means no matter how much hard disk you have, what is your RAM size, that is kind of your bottleneck, right? Because processor will create the addresses, processor will ask for whatever data it need, correct? Now processor only knows RAM, so that means processor can only create the required data references which are there inside RAM. So that means if your RAM is 8 GB big, that is your processor can only see those 8 GB of data, right? Nothing else. It cannot see anything more than 8 GB. So therefore, if you have a 2 TB hard disk, it doesn't make any difference. I mean, it kind of seems like it will not make any difference if I have a 2 TB hard disk or a 256 GB hard disk. It essentially is same, like, because RAM is 8 GB, so anyway both the cases it is same. It's not like that, but logical perspective it is kind of similar, because RAM again knows how many, what is my capacity of the hard disk, and I can take data, borrow data from hard disk and give it to processor. So RAM takes care of the other interface. If there is a reference of memory which processors make and somehow it is not present inside RAM at that moment, right? So then RAM will take the data from hard disk and then it will give it to processor. That is how the system works. Now if that is the case, you can understand that hard disk is maybe, let's say, 1 TB long or whatever, but your RAM is much smaller than that. Even if you do not go into hard disk, let us say you are playing a big high definition game, maybe GTA's latest version, or maybe Call of Duty, or maybe whatever, some good game you are playing, some Far Cry or whatever. So that game, when it is running on the system, it will be the extracted image of that, or when it is running, basically that might be in, let's say, 12 GB, 14 GB, that memory space, that kind of memory it requires. But your RAM is, let's say, 8 GB. Okay, you might not always have a RAM which is storing the whole of the data required inside it and basically giving it to processor, right? So how does that work then? If I game which I am currently running, which is live, I am playing it, and that the whole thing is, let's say, 14 GB big, and my RAM is only 8 GB, then how things are working? How and because processor doesn't know hard disk, processor who is ultimately executing the game inside, how does processor work with this 14 GB of data when it only knows that there is only 8 GB of capacity in the RAM, right? So this is where the idea of this buffer management, or this concept or this application is there at different levels of this computer hardware and computer organization. But the idea is same, which is basically you take data from a larger or outer memory unit, place it inside you being the smaller memory unit, and then you give the data to processor whichever is required at a particular moment. Later on, if some other data requirement comes, then you throw the data which you already have, which you have already given to the processor, and processor has used it up, and throw that data and accommodate the new data that you need, reference for the new data, ask for the new data from hard disk that you need, and that new data will come. Now again, if there is again new demand of data, then maybe you can again refresh whatever is there inside you and take a new data and place it in your accommodation. But you see that how to manage this, how to do this, because it can get a little bit tricky. So if I have a data reference, let's say data demand or data reference, let's say data demand addresses like this. Let's say I have, let's say 102 is one. Let us say 102 is, I mean, it is a representation of a memory address where a particular data is present, right? 102, 103, whatever, like that. It's not actually like that, but let us say for the sake of easiness. So 102 is a particular memory location where a specific data is there, and I want that. So 102. and let us say you have only 4 cells inside your RAM. Okay, 4 cells are there inside your RAM. So 102, and let us say initially you have 100, 109, 111 and 121. Let us suppose these are the 4 data, these are the 4 respective addresses. But what I mean is, when I'm writing 100, I mean the data corresponding to 100 is present inside this location. Okay, it's not 100 is not present. 100 it's an address. So when I write 100, it basically means that the data which is there at the 100th memory location is present inside this cell, inside the RAM. Let us say this is RAM buffer. Okay. Now, I hope you got that. So now if this is the initial state of my RAM, and let us say after that I want 102. Obviously 102 is not there, right? So maybe let us make me remove this 100 which is already there and place 102 in place of it. So I removed 100 and placed 102. Okay. Now let us say the next reference is 100 again. So then what will you do? You might make a mistake. Sorry. So first of all, you might say that, okay, I will place 100 over here. Suppose I placed on the second area 100. In the second cell, I placed 100. Okay. So then in the third reference, let us say again I have 102. Then again 100. Then again 102. Let us say this is kind of my memory reference. This is how processor is demanding the data. So first of all, it's demanding data at 102 memory locations. Secondly, it is after some time it is demanding memory data at memory 100. Then again it is demanding data at memory 102 likewise. So now initially when I had this, none of them, I mean only I had 100 and I removed 100 to accommodate 102. After that I took the decision of deleting the second cell and placed 100 over here. Now you see that all of them will match. I mean, no matter how many hundreds and 102 I have, it will basically be present inside the RAM buffer. But suppose instead of deleting this, I would have deleted the first one. I think let's say 109 was present, whatever was there. And I took the decision of, okay, initially 100 was present over here. Initially 100 was over here. And I removed 100 to accommodate 102. After that, I somehow took the decision, okay, next again 100 is asked, so let me remove 102 and place 100 over here again. Now you see the next 102 will again create trouble, and let's say you again took a bad decision and removed this 100 and placed 102. So then again a miss will happen, and again you have to, so every time you will miss the data and you have to reload the RAM multiple times and ask for data from hard disk. So whenever you are going to hard disk to fetch data, and whenever data is not present inside RAM and beforehand, if the data is not present inside RAM, that will take a lot of time. If you are going to hard disk, throughput of hard disk is very less as compared to RAM. We have discussed that, right? So therefore, any access to hard disk will take much more time. So if the data is already present inside RAM, when processor is asking for it, that is much more, let's say, a fruitful scenario. So because of that, we would try to maintain a replacement policy. This is, we are replacing the data in demand, right? So we will use a replacement policy. We will try to use a good replacement policy so that I can minimize the number of, and this is what we call misses. Minimize the number of misses inside the buffer. That's the idea. Now the problem is, you might think that, okay, when I'm seeing 102 is there, then 100 is there, I can see this alternating sequence is there. Why will I remove the 100 and place 102, again remove 102 when I have all these 3 cells? Yeah, the idea is you don't know, when you are reading this particular value, you don't know what is coming in the future. So you don't know these things, right? It might be something different, it might be same or whatever. So that is completely unknown territory for you. So therefore, you have to take a algorithm, a philosophy of removing the, replacing the data items. It's not that easy. You don't know what is coming in the future. So therefore, you have to basically come up with something something genius technique. So it turns out that so that is the context of this buffer management policy. Now it turns out that normally in computer access, if you see the patterns of data access, you will see there is a concept of two things are there. One is, first one is called spatial locality, and the second one is called temporal locality. So what is this thing? Spatial locality means whatever data I have currently used, currently required by the processor or currently I have used, the data present next or contiguously stored in memory has the higher probability of getting accessed in the nearest time. So spatially closed data have a higher probability of getting referenced or getting accessed or getting demanded, right, at a particular in a very near future. So that is the spatial locality of reference. So the reference has a higher probability of demanding, a particular data reference has a higher probability of of coming in case that is spatially located in a contiguous memory location or in a continuous memory location near the data which is referenced now, right? So in near future, you might reference a data which is spatially closely located in memory from the data which you have currently accessed. So that is spatial locality. Temporal locality says that this is kind of, for first timers it might seem a little bit counterintuitive. It says that whatever data I have currently used in near future, again I might need the same data. So that is called temporal locality. So if I have used, let's say, uh, some data in the nearest amount, in the very near past, then the use of, or the probability of using that data in the very near future is higher, right? So that is called temporal locality, which is timing. So it says that the data which you have used in near past has a higher probability of getting accessed or getting referenced in the near future as well. So this is temporal locality. So all our replacement policy is based upon, mostly based upon these two concepts and the access pattern. Now, what's important for you is the LRU replacement policy, which is called the least
List, yes.
least recently used. So as you can see, this is your temporal locality. On the basis of temporal locality, we are devising this algorithm. So least recently used means what? I will replace that data which is used quite a back in future. Quite a back time in the past, right? So it's not recently used. So I will try to maintain the data which is recently used. The whole idea is try to keep the data, which is recently used. Okay. So this whole philosophy is based upon temporal locality, which caters to temporal locality. But does that mean that LRU is always a good strategy? No. Obviously no, because if the access pattern is such that it makes you, in a specific access pattern, the LRU will work as the worst case replacement policy. But it is observed that most of the time, on an average, if you take 1000 access, let's say disk access addresses sequences, 1000 such sequences, you will see that LRU performs fairly good on an average, right? But in some cases, LRU will perform the worst. So if I try to, let's say we have only 4 frames. So this is the given data. So your buffer has 4 frames. Okay, and let us say initially nothing was there inside these frames. Okay, then let us say I have 100. So first of all, so whatever I need to put. I mean, since nothing is there, all 4 will be missed. So let me just put randomly what comes. So 100, let's say 102. Let's say I put 102 over here. So this is random. This is whatever comes. You basically put 103. Okay. So let's say then 100 again comes. So that will not be a miss, right? So this will be a miss. This will be a miss. This will be a miss. This is a hit. Right. Okay. After that, let us say 104 comes. So replace 104 over here. Is again a miss. Okay. Now, if I am following the LRU policy, least recently used policy. So after that 105 comes. Suppose. Right. So which one should I remove?
Sir, do we need to shift 100 at the place of 104?
Sorry, what? I didn't get.
Do we need to replace the position of 100 at 104?
Yeah, so this 105 came, right? Now I have to empty one of these 4 cells to accommodate 105 because processor is asking.
So
Sir, you are asking
104.
for
LRU.
Yeah, we are following LRU. Let us say
102.
Okay, so let us see. So 103, 104. LRU is saying that I will remove the one which is used quite a long back in the past, which is not recently used. So least recently used means what? Which is not recently used. So
100.
exactly.
102, sir.
Why
102.
100? Why 102?
Sir, because in hit we have at 100, so it becomes most recently used.
Yeah, not most. Let us say most is
Yeah,
104.
sorry. Oh, yeah, most is 104.
Yeah, nice.
Second
So
most again.
second most, exactly. The second most is 100. So don't make this mistake that okay, 100 is used over here at the first. So 100 is the most, I mean, used the maximum time in the past. No, that's not the point because 100 is used again over here. So it is beneficial or it is advisable to see the access pattern from right to left when you are figuring out which particular block to remove or which particular data item to remove. So as you can see 104, 100, 103. These are the 3 terms which are recently present just before just left hand side of 105, which is the current data that I need to accommodate. So 104, 100 and 103 are the 3 most recently used items. 102 is the one which is the last one. So therefore I will remove 102.
So why
Yes.
did you mention the missing?
Sorry, what?
The missing you mentioned, H. What is it trying to say as it is a repeating?
It is
Hit.
it means that the processor is demand. So this means what? This is basically the addresses that processor is demanding. The story I told you, right? So these are the addresses that the processor is demanding. So processor might demand the same data 2 times, 3 times. Like in this example, I told 100 and 200. So that means the processor is demanding in an alternate fashion. So here the processor is demanding this 100 again. Now since 100 was already present in the memory, so therefore I did not have to ask the hard disk to give me. It is already there and that signifies the hit.
Okay.
Right?
That's
Yeah.
called, you are saying missing, right?
That's hit. Missing is when I do not have and I am fetching the data from hard disk. So like this 105. 105 was not there, right? So here 102 was present.
Okay.
102 was present here. So 105 I am demanding. Processor is demanding 105. 105 is there inside RAM? No, it's not there inside the buffer, right? So that is a miss.
Okay.
So at this point, I will ask the hard disk to fetch me the data corresponding to 105 and I will replace or empty one of my memory unit to accommodate 105 in that position. That is a miss. That is I'm missing because it is not present there beforehand. 105 is not there earlier. I asked the hard disk to give me the data and I deleted one of my data cell to accommodate that newly acquired data from hard disk. So this is a miss, right?
Yeah.
Okay. So this is a miss. So I remove this 102 because we are following the least recently used. So 105 is placed over here. Now let us say again I have 103. So now obviously you can understand 103 is already there inside the RAM. I don't have to ask the hard disk to give me the data or anything. Nothing like that. It's already present. So since 103 is already present and I do not have to delete any other cell to accommodate 103, it is already there. So that is a hit again. So whenever you have to delete something or and accommodate a new data, or in the initial phase without deleting, there is nothing present in the RAM, it's empty. So therefore the first three were anyway misses, right? First four actually, because 100 came in between, but the first four were anyway misses. So these four, by the way, are called cold start misses. These are called cold start misses. Why? Because it is kind of, when you're starting, it is assumed that nothing is there inside the buffer. So whatever is the size of buffer, that many times misses will anyway happen because you have to fetch and fill it up. So these are called therefore the starting misses or the cold start misses. Anyway, so 103 was a hit, right? After that I have, let us say, now observe this. Suppose I have 107 as a new access, right? So which one will you remove, or let us, just a second,
100 is
yeah. So let us say next is 100, right? So you see what happens is whichever you are removing, so let's say 100 and 100 you will remove because that's the least recently used. So remove 100 and placed 107 in this place. So this was a miss. Now you see the next one is 100, right? And then let's say the next one is, next access is 104. I hope you are getting the pattern, right?
100 is also miss.
So 100 will also be a miss. So, and which one will you remove, by the way, in this case?
104.
Correct.
104.
So this one you remove to place 100, but then again the next is 104. So you see, I can have the least recently used policy, which is basically said on average performs the best, right? The LRU buffer management policy kind of, I mean, statistically speaking, it performs best. But I can have a particular access pattern just by looking at the last three accesses. I can figure out that I can figure out which one will be removed by looking at the last accesses. I can figure out according to the LRU policy which particular cell will be removed, will be replaced with, right? I just have to take care and place that particular cell as the next to next access in the sequence. If I follow this algorithm and generate a pattern by looking at the last three accesses, and from that I figure out which one is the least recently used, and then from the next to next access I place the next least recently used access address as the next address to be referenced. If that is the idea I follow to create a access pattern, then I will basically have a sequence of memory access which will be worst case scenario for LRU because all of them will be misses. And that's kind of the idea I show. Now 104 is, you have removed 104 to accommodate 100, but the next access is about 104. So this is also a miss. So just for one more repetition, as you can see, 100, 107 and 104 are the last three used. So, so let me just delete this 104. Right. So in this case, you can understand that I will remove, if in case there is something new that comes, I will have to remove what? 107, 104 are the 100, 104, 107 and 103 are the last items. So 105 was the least recently used, right? So if I set the access pattern to be 105 over here, okay, now 105 will be a hit anyway. Let's not delete that. Suppose anything which is, let's say 109 first of all, So in this case, you will remove 105, right? And then again, I have 105 over here. Right? So 100, obviously least recently used is 5. So this one, so you will remove this to place 109. But then again, you have a 105 over here. So this is miss. This is again a miss. Because then again, you have to remove one term. So you see that if I would have used the most recently used policy, just the opposite of that, then this would have been a hit. So don't think that LRU is always the best idea, but I hope you get the point that how to solve this kind of question.
Yes, sir. Like we we have to have it like solve like vertical columns made.
Vertical columns mean?
Like we solve the question of LRU like by making the vertical column like.
Acha, acha, acha. By in this manner. Okay. So that is fine. So if you have practiced well, you don't even need anything. You can just see the pattern, and from here only will
Yes.
understand which one is miss and which one is hit. Okay, so that is one question that might.
So we have to take like we have to see with three terms where we put to next.
Correct,
Right?
correct,
Okay.
correct. So this is another important numerical, and then binary search tree creation is there, which I think we have. It's kind of easy, nothing difficult. Just just keep these two things in mind. First of all, that height question, right? What is the worst case scenario of a binary search tree is height. So let us say I give you there are, let's say there are any random 56 nodes in a binary search tree, and when I say binary search tree, it is assumed that it is mostly complete, or let's say mostly complete or mostly complete, which is also called partially complete. Binary search tree, because if I do not have a binary search tree which is mostly complete, then the height can be something different. So in case of a mostly complete binary search tree, which is kind of most of the nodes has two children, right? Even nothing is given to you like mostly complete or anything, then the question can be a little bit different. So let me just okay, first discuss this mostly complete binary search tree. What is the height? If I ask you what is
Sir, like I have a doubt at this point. Like in PDSA course, we will be taking the height of the empty tree as 0 and height of the root node as 1. That convention is if there is one root node, the height is 1.
the root node's height is 1?
Yeah. Because we will be assuming height of empty tree as 0.
Okay, so okay,
But here the convention is the other way. Root node is 0, and then
yeah, because by normal definition, okay, so that might be the yeah, fine. So you follow that in PDSA. Here you follow the concept that we are saying that the number of edges is basically the height. Okay. In fact, for your general understanding, let me say this: height is always the total number of edges that you have from root node to the whichever node you are going, or in case of height of the tree, it is basically the deepest leaf node that we are talking about. So from root node to leaf node, deepest leaf node, whatever may be the number of edges and the longest path, that is basically the height of the tree.
Okay.
And that's not for DBMS, that's in general. But in PDSA, since if you see that concept also holds in PDSA, but only in the case when there are only root node and nothing else is there, in that case we are considering the height to be 1, right? Because
only root node. If there is no root node, then height is 0. Empty.
Then height is 0. Then height is 0. But if what I said is, let's say according to the edge definition, that the number of edges from root to leaf, that concept also holds in the PDSA course convention as well. Because then let's say if I have a structure like this, right?
Yeah.
So in this case, the height of this tree will be 3, and in PDSA also it will be 3.
Okay. Yeah.
Right. The same according to PDSA. That also, what is the height of this tree? You just apply the PDSA's concept.
Yeah, if we apply some graph traversal algorithm, then it will be 3.
That's what I'm saying. So if you take the idea of number of edges to reach the deepest leaf, that is kind of the fundamental idea of height, right?
Yeah.
and it will be applicable in all courses, all places, anywhere in the world. The number of edges you take from root to leaf, that is your height of the tree, and deepest leaf, okay, that is the
Okay.
height of your leaf. But only in the initial case of having only one node in the tree, PDSA is considering that to be height 1, we are considering that to be height 0.
Okay.
That will only happen for one node.
Okay.
So since mostly we will not be asking you question on one node, so basically you can assume this idea, only one idea if you want to keep in your head without getting so much confusion. Just keep the idea that height means number of edges from root to leaf and deepest leaf. That's it. Okay, so what is the height of this kind of complete or mostly partially complete binary tree?
55.
I said complete or partially complete. See, that's the idea. So a binary search tree is maximum height. In case I am not telling you these things, right? It is a complete tree or partially complete tree. So if I am not using the word complete anywhere, then your answer is correct, because the binary search tree can be something like this.
H minus 1 रखें answer.
X minus 1, huh? Dot dot dot, like this. This can be the worst case scenario of height, and therefore obviously you can understand if I have 3 nodes, right? So I will have one, I mean these 3 nodes can be like this, and I can have maximum height with 3 nodes as 2, right? So likewise I can have the maximum height with 56 node as minus 1, which is 55.
In this case, yeah, maximum height is that, and minimum height will be 5.
Yeah. So in maximum height will be 55 in case not complete.
Yes.
Not complete or not partially complete, whatever, not partially complete, right? So that is the idea. But if I'm telling you this thing, then that means most of them have 2 children. So then you don't have that one kind of linear kind of this will never happen. So in that case, what is the answer?
It will be 5.
Yeah, so that you have to be a little careful. So it will be 2 to the power, so you just figure that out. Obviously if you have 2 to the power 5 is 32, 2 to the power 6 is 64, right? So 2 to the power, it will be 2 to the power 6 will be 64, and then minus 1 according to the formula, it will be height will be 5, because the formula is 2 to the power of h plus 1 minus 1 is basically the number of nodes you have. So that is, obviously the ceiling value. But okay, even if you do not want to confuse yourself with the formula, if you can remember it, then this is the formula. I mean, if you want to do it in that fashion, it's fine. Whichever you feel easy. That is equal to the number of nodes with height h. Right, but what I prefer is just keep this thing in mind that if I have whatever is the power, so 56, the next higher power of 2 is 64, right? So if
Yes,
the next, yeah, so if the next higher power of 2 is 64, right? So that means what? 2 to the power 6 is 64. So since it is lesser than that, and height will be just 1 less, as we already know, whatever may be the number of nodes. So I will have 1 less than that. So 5 will be the height of the tree. So that's how you can do this. Okay. So, but if I ask you the question without any information regarding complete or partially complete or anything, so in that case, the height can have 2 values. First of all, minimum and maximum height. So then the question might ask you, what is max height? Or let's say we can ask you something like that. Kind of a making a little more fashionable. Let us say x equal to max height, y equal to min height. Okay, what is x plus y or x minus y or something like that? So then you have to figure out both these two, and a numerical answer type question. Stuff like that can come. You can understand maximum height will be 55, minimum height will be 5. So then you do it accordingly. Okay, so that is binary search tree related to height. Another thing is, by the way, in PDSA, you guys have reached trees, right?
Yes, sir.
AVL tree is also done or not done?
Yes, sir.
Yeah,
Done, sir.
understand.
Okay. Atul, I think Atul sir is there, right, in PDSA?
Yeah, Atul sir and Satyanarayana sir.
I left PDSA after that. Satyanarayan sir took up. So okay, so AVL tree is also done. But then you guys are anyway comfortable with those concepts. But those who have not done PDSA, don't worry. When you do PDSA, we learn this thing in proper detailed manner. Okay, so the next important thing is creation of binary search tree. What is the time taken to create a binary search tree for those who have done PDSA? For those who have not, do not worry.
Logan.
Login is the time taken for creating binary search tree. What is the time taken to create a heap?
No, no, no.
Now, what is the time taken to create a heap of n elements? Tell me that.
You mean insert operation in a heap, is it?
No, I'm saying create a heap.
Creating a heap is just order of one, right? Just initializing the array.
Is it?
Is it order of n?
It's order of n, correct. It's order of n. Why? Because your build heap, when you have to do, you will have to actually make the initialize the array may not be always in heap manner, right? Then you have to take the leaf nodes, and on each leaf node you have to call heapify, and then heapify will go towards the height, and that will take log n time. But if you take amortized analysis, you are basically taking order n time. That part is kind of very interesting. So that's why I asked. So I don't know whether that discussion has been done or not, but creating a heap is order n time task. But if you say that you want to do n, I mean some x not n, some x amount of insertion operation in heap, then that is x into log n time. So each operation is log n time, because heapify is essentially log n time. So that's why. But creating a heap is order n time. Okay. Coming to the next point, which is creating a BST. So just tell me some random numbers, just for the sake of completeness. I am discussing this. Some random sequence of integer numbers. Let's say 12. Then
15,
15.
17.
Hello.
32 will repeat.
Yeah. Yeah, you're audible. Tell.
Sir, actually, I have a question. If we get 35 nodes in a binary search tree, so how many, what would be the height of it? Like, will be taking it as 2 to the power 5 or 2 to the power 6?
So that means what? 35 means what? 35 we will obviously, if you have 35, that means what is the highest value, upper value of 35? I mean 2 to the power 64, right? So if the 6, yeah, so if 6,
I want to know the height. What would be the total height of the binary search?
that's what I'm saying. If 64 is the, I'm telling that, right? So it can be maximum height will be 34. And minimum height will be what? If it is not telling you about complete binary search tree and only asking, the question is only asking you if 35 nodes are present in the tree, what is the height of the tree? First of all, that is an incomplete question. So it will tell you complete tree or incomplete tree. If it is not telling you that, it will tell you whether it is maximum height or minimum height. Because if you are not mentioning about whether the tree is a complete tree or not, then you have to tell me about whether it is whether I'm talking about max height or min height, because max height can be 34, right? In case no information regarding completeness of the tree is given. And what will be the minimum height? Minimum height means basically when I consider the tree is kind of complete or at least partially complete. So in that kind of situation, what will be the height? Obviously, the next power is 64, which is 2 to the power 6. So it will be your 1 less than that, which is 2 to the power 5. I mean 5 will be the value. So if you also think the tree, right? Not by enumerating, I'm just giving you one detail. So let's say at height 1 over here you have 3 nodes, right? At height 1 over here till this point you will have how many nodes? 4, 5, 6, 7 nodes at height 2, right? So that means you can see that it will be, if I say what is the height 2, increase the height by 1, which is 3. 1 less than that is the total number of node at this level, right? So if I tell you I have 9 nodes, suppose if I tell you a binary search tree with 9 nodes, so that means what is the highest power? I mean higher power than 9, I mean higher power of 2, which is nearer to 9. So you will get the next higher power of is after 8 I will have 16, sorry, 16, right? So 2 to the power 4, so less than 1, which is 3. So therefore the height will be 3. So as you can see, if I have 9 nodes, so that will be basically this tree.
Okay, sir. Just one question more.
So then the height will be 3, right? 1, 2, 3.
Yes, sir. Yes, sir. That I understood. Just one question more. In the question, we would be specified that we have to find the maximum height or minimum height.
It will be mentioned obviously, otherwise the question is incomplete. Either it will tell you that the tree is complete or by mostly complete. In that case, there is no question of maximum or minimum height, because the answer will be whatever is the minimum one, because the tree is complete. In case it is not mentioned, then they will, in case it is not mentioned whether the tree is complete or not, then they will ask you in the form of find the maximum height possible, find the minimum height possible, something like that. Otherwise, the question is incomplete. You can raise your, let's say, concern after the exam.
Okay. Thank you, sir.
Yeah. Okay, so if this is the sequence, so let us create a binary search tree. By the way, in the meantime, those who have done PDSA also try to think of some use cases, real problem statement where binary search tree is needed. Okay, not now, don't tell now, let me just complete this. Fine, so how to create a binary search tree, that is important, another kind of question that might come. So first is the root node 12, so make it as the root node. So first one is always the root. Okay, first one will always be the root node. So 12, and then after 12 I will have to arrange the numbers in the order that if I get a number which is larger than the current number on which I am residing, then I will place that on the right hand side. If I get a number which is smaller than the number on which I am currently present, I will place that on the left hand side. So now I am currently there on 12, and the next number is 14. So obviously 14 is greater than 12, so I will place 14 on right hand side of 12. Okay, fine. After that I have 2, right? So again, and okay, one more important point, every time you place a number, you will start from the root node. Okay, you don't start from the last entered number. You always start from the root node. So for every number over here, which I will enter one by one, one after another, I will start looking the position of entering that number from the root node. Always start from the root node. So now I have to insert 2. So I will start from 12 and see where should I place 2. So 2 is smaller than 12. So I will put 2 on the left hand side. Again 15, start from 12. Always start from root node. So start from 12. 15 is larger than 12. So I will go on right hand side. So go right hand side. Now you have another number over here which is 14. So 15 is larger than 14. Yes. So therefore place 15 on right hand side of 14. 17. Same thing. Start from 12. 17 is larger than 12. Yes. Go right hand side. 17 is larger than 14. Go right hand side. 17 is larger than 15. Go right hand side. 17. So 20. Same concept over here. 20, 32. Right. 18. 12. 18 is larger than 12. Go right hand side. 18 is larger than 14. Go right hand side. 18 is larger than 15. Again go right hand side. 18 is larger than 17 as well. Go right hand side. but 18 is smaller than 20. So at this point you see that 18's value is smaller than 20. So smaller value comes on left hand side. So I will have to, since I've reached 20 now, and now I will come to left hand side, which is 18. Okay. 4, same concept, go left hand side. On 2, 4 is larger than 2, so go right hand side. 1, from 12 I will go left, from 2 I will go left again. And finally 28, which is I will go till 20. Obviously you can understand same pattern. From 20 I will say that okay, 28 is still greater than 20. 28 is still greater than 20, so go right. And then 28 is lesser than 32, so go left. So this is binary search tree, and the height of this binary search tree is 1, 2, 3, 4, 5, 6. Right? Yeah. So this is how you create BST. And as I already told you, BST, the idea is BST, if you it keeps the data in a sorted fashion. How it keeps the data in a sorted fashion? So if you basically look from top or look from bottom, basically you look laterally from top or from bottom, it will be not laterally. What I mean is you look either in one direction from top or bottom, you will see that all the numbers are arranged in a sequential sorted fashion. Right. So if you just map all of them together, now this is kind of not drawn in a proper manner, but yeah. So this, now if you arrange all the number on this number line, so that is a normal increasing order. Right. It will never happen that this number and this number are not in increasing order, or any two random number on this number line will not be in increasing order. That will never happen. It will always be in increasing order. So that is the facility of binary search tree. It always keeps the record in a in order traversal. So those who don't know what in order traversal are, but basically, yeah. So this is the idea. If you look from the top or bottom, it will store the thing. It seems like it is a kind of sorted array, right? Okay. But
Sir, this is example of partially complete.
This is partially complete. No, this is kind of in middle, but you can say it is partially complete. Anything which is not the worst case is said to be partially complete, but this is also not a correct definition of partially complete. Okay, so, but you don't have to worry about all of that, because whenever we will ask you a question regarding partially complete or something like that, you basically consider it as a complete binary tree and you go ahead with it, right? But we will not show you a tree and ask you whether it is partially complete or not. That doesn't make any sense. So yeah, but it is not, properly speaking, this is also not a partially complete as well, because partially complete's exact textbook definition is only the last level can have some extra nodes. So what I mean is, I will have all the nodes filled up with two children. Only the last level, let us say this is the last level. Here I can have something like this, some absurd pattern like this, which is not complete. Then again,
and complete is fully balanced, right?
Complete is to the last level, it will be balanced. Right, but those things doesn't matter for you in at least DBMS, because the question will come in a very specific types that I already discussed. Okay, because we can't do a lot of tricky things, because most of you have not done PDSA, but in PDSA we will do many things, and then we will ask multiple kind of questions on these topics. Anyways, yeah, so this is basically all the concept of week 8, and that is important with respect to week 8. Other than that, just go through a little bit of storage. Those slides where storage devices are given, what is volatile memory, what is non-volatile memory, some just a little bit of trivia, because one question might come, might not come. But a few questions will come from this hard disk access, that is for sure. Two question might come from this hard disk. One question from LRU replacement will come. Binary search tree, one question will come. So 4-5 question, 3-4 question at least will come for sure. All these topics. Yeah. Any doubt in all this thing? Otherwise, I will move to those initial week 5, week 6 concept. Okay, fine. Yeah, just for those who have done PDSA, I think I asked how, where are some, give me some real situation where BSTs are used.
We can use it for database indexing.
You can use it for database indexing. You can use anything, but what I'm trying to think is, but what is the ultimate selling point of using a BST? I can use a normal multi-level thing, right? How BST will help me?
If ordering is there in the data, we could, in the ordering is there in the set of indexes, like we can easily navigate, right?
Yeah. So basically, you will be able to find any number in log n time. That's binary search tree will help you with that. Nice. Okay. Chalo. So let us go back to this. Dependency preservation is one concept. Overview of decomposition. Okay. 4NF, PCNF. Okay. So let me just. So what is dependency preservation? By the way, what are dependencies? First of all, functional dependency, not with respect to your, let's say, how to solve these questions and all that. I hope you guys know at this point. But functional dependencies are basically business logic. Okay. So, and again, I say this in most of my session of this functional dependency and normalization, because most of us have this wrong idea of having functional dependency, that wrong idea that we always generate functional dependency from the table. No, that is not correct. In real life, functional dependencies comes first and the table data comes later on, which follows the functional dependencies anyway. Okay, but in our, I mean, curriculum, when we are asking question, we have to frame question. We cannot, I mean, it will be very difficult if we kind of give you a huge business a use case with this requirement and ask you to figure out which are the functional dependency from that discussion, which is kind of a comprehension based question. Okay, so it will be difficult for you guys to answer in that time frame, and where we want to test multiple concept also. So, but yeah, that is the idea. The real thing is we will give you a comprehension, which is basically a discussion between a client and, let's say, uh, the IT people. They are discussing it, something, and the client is telling you these are my requirements, some business logic that they want, and those, on the basis of those business logic, you create the constraints which the data inside each table should follow. So that constraint, that those multiple constraints that you are creating, which according to which the data will be populated inside the tables, those are functional dependency of that particular table. So it's not like you see the data and create functional dependency. It's rather, in real life, it's rather the opposite way. You discuss with your client, create the constraints. These constraints are nothing but the functional dependency, and on the basis of that you populate the table. Basically, you create the table having those constraints, so that the table are later on populated by following those constraints. Okay. So that is the most important idea that you must have before you complete this DBMS course. That functional dependencies are not created from table data, but in our problem solving kind of situation, obviously we are asking questions, so that you have to figure out functional dependency by looking at table data. That is fine, but that is not what happens in real life. Okay. So yeah, having said that, now let us get into the functional dependencies. So what are functional dependencies? Basically, if you have a repetition value, so if I say if I say that A functionally determines B, that means whenever the value of A will be repeated, the value of B, let's say B, C, D, the value of B, C, and D individually should repeat. All of them should repeat, right? Whenever the value of A is getting repeated in the table. So that is basically the meaning of functional dependency. Now let us take this example. What is dependency preservation? Now dependency preservation means, as we already know, functional dependency. If we are able to preserve a dependency after breaking the table, so we will know as a part, we already know that as a part of normalization, we will have to break the table into smaller subtables in order to achieve different normal forms. And why do we do that? Because each normal form, as we go to higher normal forms, we kind of eliminate higher levels of redundancy in the table. So if I want a very, let's say, proper table with no redundant, not no, basically very little redundancy, I have to go to the next higher normal form, the highest possible normal form that I can reach. But as it is seen that as we move on to higher normal forms, there are some other troubles that come, that you will break down the table to such an extent that it might become little bit difficult for your join operations to be done later on. So because of all those things, it is a trade-off. I mean, having a little bit of redundancy without complicating life so much, without creating hundreds of tables. Again, the other way, if you do not have a proper, let's say at least if you do not if you do not eliminate a considerable amount of redundancy and keep things together into, let's say, a few tables, then again it will lead to multiple anomalies, insertion, deletion, and update, and all those things. And that is quite evident because redundancy is there, so you might not be able to update one information in all the places, right? You might miss it, which is very proper and very observably happening in different government, let's say, government this course that are running currently and previously as well, that this person's data is there inside that particular record, but it is not there in that year's that particular record. So there are thousands of places where a particular person's record is there and thousands of other places where it is not there, because there is no centralized system and therefore there is redundancy. And because of this redundancy, there is a lot of confusion later on, legal battles and stuff which goes on, right? So therefore, in any modern database system, our main target is to eliminate redundancy. But then again, the question is till what extent? It might, your life can become difficult if you go on eliminating redundancy to a level of more than 90%. So anywhere between third normal form to BCNF is a very good state. Okay, third normal form itself is a very good state. BCNF can sometimes prove to be a little bit difficult for some situation, but yeah, 3NF and BCNF are anyway very good positions that you can maintain in your DBMS database management system in order to have a proper database. Okay, and the higher forms like 4 normal form, multi-valued dependency, and 5th normal form, all those stuff, there are multiple normal forms as well. These are very case specific requirement. In some cases they are used, mostly they are not used. Yeah, having said that, now dependency preservation. So why dependency preservation is important? Because as we discussed, dependencies are basically business logic, right? Now, in order to do normalization, in order to reduce redundancy, you broke the table at such an extent that you lost some business rules which should have been followed while populating the table. That's the idea. Because let us say a table had, let's say, at first 25 attributes, 25 columns, and on the basis of that you had some specific rule, compound rules, basically, let's say 2-3 columns on the left hand side of the dependency and 2-3 columns on the right hand side of the dependency, that if this value of this particular column is this one, and along with it, if the third column's value is also this one, then the 8th column should be this one, something like that. You have some kind of dependency like that, and you broke the table into 3 column table, right, subtables. So then you don't have these many columns together at all, and therefore you will anyway lose the dependencies which basically constituted multiple columns together. So while decomposing tables, since we are also separating out the attributes, or basically the separating out the columns, we can lose dependencies in the process. Yeah. Okay, so we can lose dependencies in the process. So if we lose dependencies in the process, then that is not something quite desirable. We will try to minimize that as much as possible, because losing a dependency basically means you are losing a business logic that the client wanted to be present, right? So that particular business logic or that particular requirement of the client about his data will not be, let's say, adhered to. right? So therefore, we don't want dependencies to be lost while doing decomposition. Uh, so we will try to preserve that. Okay. Now let us see, that is the context of dependency preservation. Now let us take a few examples and see whether dependencies are preserved or not, and how to check whether dependencies preservation is there or not. So one classic example is this. Let me discuss that first. Right, let us say we have this table ABCDE relation, and I have the functional dependency A goes to B, B, C, C, D, D, E. Fine. So we have this dependency structure. Let's say I call it F. Okay, functional dependency on the R table. So F on R. Right, and then I decompose this table into sub table. Let's say R1, which is AB. Fine. So this is how I divided the table into smaller 4 tables, subtables, because of normalization. And we know that while decomposing a table, it should be a lossless decomposition, and the condition for that being that I should have, when I am dividing a table into 2 subtables, the common attribute, there should be a common at one or more common attribute between these 2 subtables, and the common attribute should be able to serve as a key to at least any one of the table. If it serves as a key for both the table, well and good. If it is not serving for both table, at least one of the table, either among the 2 table, it should serve as a key on one of the table, one of the subtables, right? So the formal way to mention that, if I am dividing a table R, let me write it over here. If I am dividing a table R into R1 plus R2, so in that case, what I mean is R1 intersection R2. I mean, when I'm saying intersection, I mean the columns or the attributes. So R1 intersection R2, whatever it is there, that should serve as a key that should functionally determine all the attributes of either R1 or R2 or both, basically. So yeah, so this should be followed while decomposing a table into R1 and R2 for lossless decomposition.
Sir, the relation is basically is derived from the functional dependency, right? So we can take what are the functional dependency. So from there we can make it as our own conception as our own R2 or 3 like that.
Yeah. I mean, in case whenever you are doing normalization, you will anyway follow the rules of normalization and it will work perfectly. But if I give you a question with already the decomposition, like in this question on the left hand side of the screen, that I have given you a decomposition, and then I might ask you 2 questions, that is the decomposition given to you whether it is lossless or not. So in that case, you have to, or I can also ask you whether it is lossless and whether dependency preservation is there or not. So then you have to figure out whether the decomposition is lossless or not by applying this condition.
And E to A also R5, I thought like you didn't mention that.
No, I don't want to mention anything because all the attributes are covered, right? A, B, C, D, E is covered. Why will I again have another table with E and A?
Oh, okay.
Right? When I'm breaking it up into tables, the idea is not what is the FD. The idea is I have to incorporate all the attribute. The attribute should not be lost. Now, if I am breaking it into pairwise attribute, again I have to have a common in order to have lossless. So therefore I have this BB common. This over here I have CC common, DD common. But since with 4 tables I am able to cover all the 5 attributes, therefore I don't want another table.
Got it.
Right?
Sir,
Could
you please repeat once how you broke the table into R1, R2? I lost the connection for some time.
Okay, so it's not, we have not, I mean, I have not told anything that this is the logic for breaking the table. The question is that our table is given and then it has, these are the functional dependencies on the table R, and then this is the way I am breaking the table. Okay, so this is basically the topic is preservation of dependency.
So is there any process in breaking R1 into A and B, or you have just written like that?
No, process is there. That is the whole normalization process. But in this case, I am not discussing normalization. I am discussing dependency preservation. See, the thing is, let's say you have been given a big table. Now you want to eliminate redundancy. Now in order to eliminate redundancy, you will have to break the table, decompose the table into smaller table. There is a specific set of rules which you will follow to decompose the table in a specific manner into smaller tables in order to reach second normal form, third normal form, BCNF, all these things. Now, when you follow those rules and break the table, that breaking of the table, that decomposition of the table will anyway have a rule that you are asking for. That is there any specific rule to follow? Yeah, that rule is there, but that is not just for decomposing the table. You have to decompose the table and according to the rule, and but the idea is not just for decomposing the table. The idea is to reach a particular normal form to reduce redundancy. Now, in order to do that, the tool is decomposition. So you decompose the table to reach a particular normal form in order to eliminate the redundancy, and those rules are followed, and therefore you will decompose in a specific manner. But that is a separate discussion that I will do after this. But before that,
here you have taken R1, R2, R3, and 3.
Here I have taken a normal decomposition. These are the 4 subtables, and I am asking you whether
only considering the common one of the common.
Correct. Right. This is a random decomposition. I am asking you whether this decomposition holds the dependencies, preserves the dependencies or not. That is the question.
Okay, sir.
Yeah. So these are the 4 tables, subtables, and the question is dependency preservation held over here or not? Are all the dependencies present in these subtables, or am I losing something? Now you should be very careful about, conceptually you should understand when I am asking you the question whether dependency is preserved or not. It's not just about solving this question by some technique. No. What am I really asking? I'm asking is these are the rules according to which the table A, B, C, D, E, the data inside the main table, the original big table with 5 attributes, the data inside this table was such in such a state, was in such a, let's say, interrelation with each other, the rows of the data inside the R table, that they were following all of these functional dependencies. I can apply these functional dependencies to any row of the table R, and they will hold the value. They will hold true, right? But when I divide the data into this 2 attribute table, R1, R2, R3, R4, now again I will have 2 columns of data in each table. Now my question is, now in these subtables, are all those patterns which were initially followed still followed or not? But now you will ask the doubt, okay, but now the attributes are not together. So how will I relate between 2 attributes? How will I relate the relation between, let's say, AB and CD? Let's say here ABCD was together, and I can have an interrelation, a dependency. Relation means what? A dependency, something like this. Let's say AC determines BD. So here all the attributes are together, and I was able to see from the table that any data in AC, let's say A, B, C, and D, suppose, right? And let's say I can figure out that if A's value over here and C's value over here is repeating, together both of them are repeating as a couple, then I will also observe that B's value over here and D's value over here would repeat as a couple, right? That I can observe. But here now ABCDs, all 4 are in different tables. Now how will I relate? There is no concept of common rows. Here it was in 1 row, right? All these things was happening in 1 row. But here is, when I'm separated out, there is no concept of a common row, and therefore no concept of having AC repeated means having BD repeated, right? So then having CD repeated, or whatever, basically. I hope you got the point. So the point is now, how will we figure that out? How will we know that the dependencies given in FR over here are all preserved? So that is the question of preservation of dependency, that is it preserved or not, how we figure that out, because by looking at the data it might not always make sense. I hope the concept behind this question is clear. Okay, now how to do that?
Sir, if we are able to get B from A and A from B, then we can say that it is preserving.
Yeah, I will. So that's what I'm discussing. Yeah. So how to basically solve this kind of question where it is asking you about whether dependency is preserved or not. First of all, that step one is you apply the dependencies which are applicable directly on the table, right? So as I can see, A and B, these are only constituting two attributes, and luckily I have a table R1 which has both A and B together. So therefore, this functional dependency will anyway be held inside AB, because the data patterns between A and B, the interrelation of data between A and B in the original table will be maintained in R1 as well, because R1 has A and B together. So A and B will be, it will be holding. BC, A and B is not lost. The interrelation of data between A attribute and B attribute in the original table will be maintained in the R1 table, and therefore in this decomposition as a whole, as a collection of R1, R2, R3, R4, this pattern will not be lost. Same concept for BC, CD and DE, because all of them will be applicable in the respective table. So step one in case of dependency preservation check is apply the dependencies directly to subtables where possible. Possible means all the attributes of that particular dependency should be together inside one table. That's the idea. So A, B, C, D, C, D, all these four are applicable. A, B over here, B, C over here, C, D over here, and D, E over here. So all these four are done. But E, A cannot be applied to any table. Right? So I cannot have the pattern, the interrelation of the rows of data between E attribute and A attribute. I cannot see that in any table, because E and A are not there together inside any table. So is E lost or not? So is the pattern or interrelation between the rows of data between E attribute and A attribute in the original table, is that lost or not? So that's what we have to figure out. Now how to do that? So that is your step 2. So in this case, what we have to do is we have to figure out in each table, right? Now, just we have to find closure set of dependency in each subtable. So what is closure set of dependency? I think that has been discussed in the normal session as well as the revision session, but maybe in the normal session, obviously it should have been discussed. So what is closure set of dependency? Closure set of dependency means what are all the non-trivial dependencies that you can figure out from the available dependency given to you inside a table. Again, I am repeating, what are all the non-trivial dependencies that you can derive from the dependencies which are already given to you inside a table. Okay, that is the closure set of dependency. Now, how to find that? So let us see. So first of all, we will do for R1. And the way to do that is you have to consider all the attributes of the table or the subtable which you are basically, for which you are finding closure set of dependency, and consider all the attributes of the table one by one, then pairwise, then 3 at a time, then 4 at a time, likewise. So for example, on the right hand side I am writing, so let us say if I had a table which had, let's say R is a table which had, let's say 4 attributes A, B, C, D, suppose, and I'm trying to find out the closure set of dependency for R, right? In that case, how will I find it? First of all, I have to find a plus, right? Some value will be there. Then I will have to find b plus, right? Likewise, c plus, d plus, right? Then I have to find ab plus, bc plus, cd plus, ad plus, all the possible combination, ac plus, bd plus, right? So this is what 4 combination 2 possible cases will be there, right? The 6 cases will be there. So I think I have covered all of them. So yeah. So these are the 2 pairwise we have to consider. Yeah. So then you have to consider 4 choose 3, or I mean all the 3 triplet wise, A, B, C, B, C, D, A, D, B, likewise, dot, 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 whatever. So 4 choose 3, which is basically your 4 combinations will be there. So all those 4 combinations you have to figure out. And then last ABCD is kind of trivial because ABCD will anyway derive ABCD all 4 trivially. So that is anyway there. Don't worry. So therefore, what will be the other one? ABC, BCD, ADB, and CBD, right? No. ABC, ACD. Right, okay. So these are the 4 combinations. So 4 plus 6 plus 4. So these many closure set you have to, I mean the closure you have to find, and then with that you can go for the next step. So this is basically closure set of dependency. If you have all these things together with you, then this whole set of data that you have, that is basically closure set of dependency. So that means that contains all the dependencies that can be present inside the R table. Okay, so this is how you find closure set of dependency, and that's what we will have to do as a step 2 of checking dependency preservation is there or not. But as you can see, the tables are small over here. So in case of R1, I will have to only check for 3 cases, which is A plus, B plus, and AB plus. Now AB plus is trivial because AB only 2 attributes are there. So therefore AB plus will anyway be AB plus. So I will be removing that also. So what is A plus? So it will be A and B according to these rules, right? So by the way, whenever you are figuring out the closure set of dependency, you have to figure that out from the original set of functional dependency given. So it will be AB. B will be what? So what is B plus? So first of all, B will be there, and then
E, D, E, A.
yeah. So B goes to C over here, then C, D, D, E, E, A. So B, C, D, E, and then A as well. Right? Now the point is, if that is the case, A was also like that. A was also A, B, C, D, E. But I will only consider the ones which are present inside the R1 subtable. So delete all of the other nodes. So I will delete C, D, and E, and only take B and A. Let me just write it in a compact way, B and A. Right? So these are the nodes that I have. Sorry, these are the dependencies that I have. Same I will do for R2 as well. Closure set dot 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 closure set of dependency. Same thing, B plus and C plus. It will be B, and then as you can see, B goes to C. So C, and since this table R2 has only B and C, so I'm not checking other things. Now C will be C and what? C goes to D, D goes to E, E goes to A goes to B. So therefore C and B. Right. Likewise, I'm not doing it for all of them. As you can guess, for R3 it will be C and D, and D and C. For R4 it will be right? So now I have the closure set of dependency of all the 4 subtables. So this is your step 2. Okay, now what is step 3? So your step 3 will be, in order to check dependency preservation, that is, let us call this set as f1, f2, f3, f4. So is f1 union f2 union f3 union f4 union, in case you have multiple such subtables, whatever, union fn, is that equal to fr or not? So this is your dependency preservation. Basically, you are checking if the initially given table, whether that is holding or not. I mean, all the dependencies of that table are holding when I'm when I'm doing a union of all the dependencies present in the subtables as well or not. So this is the check that you will do. So let us check that for in our case. So we were basically checking for other dependencies, it was anyway preserved because they were directly applicable. EA was the one under doubt. So let us check whether I can derive as a union of all these dependencies. Can I derive E determines A?
Yes.
Yeah. Why? Because if I have E, let us look from E, because if I want to check whether E determines A or not, I have to start from here because this table only has E. So I will start from here and I see E determines E and D.
D.
Yeah. So that means E is determining D from this table. Now I will not look at the top, this one, right? Don't look at this one. This is the one you are checking whether it is present or not. So don't look at this one. You will only look at this small f1s, f2, f3, f4s, the ones which you have derived. So from them you see that E is determining D, and then D is determining C. Over here D is determining C, right? So from D I can go to C. From C I can go to B over here, and from B I can go to A. That means E is basically defining A, and so I can say that when I'm doing a union of all these dependencies, I'm getting the FR dependency because this is preserved. E determines A is preserved. Now, in case I do not have this cyclic nature, right? You can see this A, B, B, C, C, D, D, E, E, A. Again, you reach to A, B, B, C, C, D, D, E, E, A. Once the A comes, you can again start over here, right? But if I remove this dependency now, if I just ask you the same question and maybe just break the chain somewhere over here, then it will not be anymore. I mean, it will not preserve the functional dependency. Getting the point? So then, because you cannot, the only reason you could derive this is because you have this chain, and that's why while you are defining using A to B, you can also go the other way and say B also determines B and A. I mean, A determines B, B determines A, C determines D, D determines C. In all the tables you had this thing because it is cyclic. So no matter at what end you start, you can reach the other one, right? But if I break the cycle of the functional dependencies, so like the one which is presently there on the screen, now this will not be able to preserve the E determines A functional dependency anymore. So this example will be an example of where dependency is not preserved. But as soon as I complete the cycle and say D determines E, this becomes an example of a question where dependency is preserved. I hope that kind of clears all of your doubt.
So dependency preservation requires the candidate key. If that is functional dependency is there. Can we say that?
Dependency
The left hand
preservation?
side.
What?
The left hand side candidate key, if it is there, the dependency will be preserved.
No. It's not. I mean, left hand side candidate key. That's something. I mean, candidate key is basically on the whole table. When you are breaking it up, the candidate key anyway doesn't make any sense because then there will be 4 new candidate keys.
In the real time example, it's not possible now. So all the attributes which are given A, B, C, D, E. So all the it determines this one and that one. So everything is here as we can say that candidate key here, right?
I'm not getting actually what are your...
No, the thing is like here A B C D E everything is a candidate key in this example.
Acha, yeah, okay, fine.
Yeah. So that's what I'm asking. So
No,
which scenario it's not?
that's not always required. In this example, it is so. I will take another example and show you that that's not always needed. For some other dependency preservation, some other example dependencies will be preserved. But
Yeah.
for let us take this example. I don't know whether it will be preserved or not. Just sake of practice, let us take one example. If I have a table R, A, B, C, E, or E, sorry. And initially the F R is, let's say, A, B, C determines D and E, and D determines E. Okay, and my decomposition is, first is R1, which is A, B, C, D, and R2 is T and E. So if I see this example, so as you can see, ABC is directly applicable on this table. CDE is not directly applicable, but DE is directly applicable. So CDE I have to check. Okay, so let us check for CDE. So same step, R1 we will derive all the possible cases, right? So actually let's do it fast. So A will be A, B, C, and D as well, right? A, B, C, D. Yeah, B will be nothing, only B.
B will nothing, yeah, only B. C will be D only.
D, E, because E is not there, correct? So D.
Yeah, D.
And
D is D only.
yeah, and AB we will let us, for now let us keep that. Let us see if we can do it without that later on. We will figure that out too. For you it will be needed. I'm just trying to do that a little bit early. Let us see what happens.
Yeah.
R2 when I'm doing for, let's say, D and E. So this is anyway DE, and E is only E, right?
Yeah.
Okay. Because there is no cycle or anything, so it doesn't work. So E is only E, D is DE, fine. Okay. Now I have to figure out whether I can take C and I can do a union of these two and reach C determines DE. So if I have C and C determines D is there inside this dependency, right? And D determines E is there inside this dependency. So that means if I do a union of F1 and F2, so that works. So F1 I am having C determines D, F2 I am having D determines E. So that basically means your C determines D.
So that's a transit you are saying, right?
Yeah.
Okay.
Right. So therefore, using this transitive nature, I can say that functional dependency C determines DE is preserved in the decomposed tables as well. It may be separately, but still the interrelation between the data is preserved in separate manner. Okay, so now you see that here it is not any cyclic or the candidate key, nothing. We did not even find the candidate key, right? But we could check that the dependency is preserved. This
So
one
this is normalized after R1 and R2 so that it is preserving. Can you say that?
Yeah.
Sir, but if we do canonical cover on this FR, that time E is like an extraneous attribute, right? So we can just simplify C determines D to C determines D.
Sorry, what? If you do canonical cover on what?
C determines DE. E is a extraneous attribute, right?
That is a different thing, right? So that's I mean,
We
yeah.
can minimize it and then we can check for dependency preservation. That time we can get direct dependency, is it or no?
Okay, so this one I would say, whatever the question state is given to you, it's better to apply dependency preservation on that, because in real life it is better to do minimization of dependency preserve. I mean, first do canonical cover and then you apply dependency preservation check in order to see whether dependencies are preserved or not. But in question, we might have asked you the question at a particular state of the table, and if you do that kind of stuff, it might not match with the answer. I mean,
Okay.
your concept is clear, that's not the point, but I would recommend you to apply just what the question is asking you, because we might just want to test your that knowledge, that whether you know how to preserve how to check dependency preservation or not. So that's the point.
Okay, got it.
Yeah. Okay.
Sir,
Huh.
if we extend this question to that, to which normal form this table to be broken so that the dependency is preserved, then how to take that?
Fine, so let us check that. So basically in that case, we have to figure out that which normal form it is currently present, right? And in order to do that, I have to check what are the candidate keys of the table. So what are the candidate keys? Right? First thing that you have to do is you have to check the candidate key. Any normal form, you have to check first step is check candidate keys. Whenever you are talking about normalization. So what are the candidate keys of this table? So if I just remove all of this, okay, because now subtable concept is not there. You are asking me to breaking it according to the, I mean, normal forms
Taking
rule.
it to the normal form so that the dependency are preserved.
Yeah. So that we will see. So candidate key. So one general point is that if you decompose till third normal form, dependency will be preserved. Okay, BCNF dependencies are mostly destroyed. Okay. Till
But
third.
sir, it is it confirmed for all the cases of the table?
Yeah. Till when it is a theory. I mean,
okay.
Yeah.
And for BCNF only it's a cyclic. Dependencies are cyclic.
No, that's not always the reason. That's not always, I mean, compulsory.
Like in sir previous example.
Previous example it was.
That is BCNF and.
Yeah, previous example it was like that. That is okay. Because
so
it
can
was.
we say that the dependencies are cyclic?
That's not always required. In this case, you can say that it is BCNF. Dependencies were cyclic, therefore it was meant, but that is a specific case. Like in this case, I showed you already that it was not cyclic or anything, but it was dependencies were preserved.
But
right?
It is not BCNF, no, right?
No, it's not BCNF. But then you cannot always say that so in BCNF dependency can be preserved, may not be preserved.
Yes, sir. That is my question.
Yeah. In BCNF, you can also sometimes see that in BCNF, along with it, if I have cyclic dependencies, all the dependencies are cyclic, then you have to think that are all the tables having all the attributes? Point number one. Are all the dependencies cyclic? Point number two. And is it in BCNF? Point number three. If all these points are satisfying, then it will anyway be preserved. Because then if it is cyclic, then basically, and in BCNF, and you have all the tables with all pairwise attributes. So in that case, you are anyway in a cyclic and there is no way you can move out of it. So that is true. That is true. That is inherently true that dependencies will be preserved. Right. So that is correct. But
okay. But the table, the broken table should have all the
attributes, all the pairs of attributes. Right. So, okay. So now checking for candidate keys. What are the candidate key of this table? So best way to check for candidate key is just check the right hand side. Step one is check the right hand side. E, D, B, C. These are the attributes. So E, D, B, and C are there on the right hand side. So if I need to have a candidate key, A must be there compulsorily as a part of the candidate key, right? Because A is not there on the right hand side. So no one can derive A. So A must be there in the candidate key itself. Okay, now if I have A, then what can I have because of having A? Because what can I derive because of having A? So I can derive B and C. So if I can derive B and C, with C I can derive D and E. So that makes the whole cast of the cinema. So I have all the candidate key is basically A. So in this case, there is only one candidate key, and that candidate key is A, right? Okay. So now if I have only one candidate key and that is A, there is no question of partial dependency. What is partial dependency saying? Partial dependency is saying in case you have a candidate key with multiple attributes, and or even if you have multiple candidate keys, so in that case none of the prime attribute, your prime attribute should not define another non-prime attribute. That is the whole point, that any part of any one of the candidate key, or any subpart, it's better to say any subpart of any candidate key, which is basically a prime attribute. Subpart of any candidate key means a prime attribute or a group of prime attribute, whatever. So that should not functionally define any non-prime attribute. If it defines, then it is a partial dependency.
Sir, what if in the left hand side there is a prime attribute and one non-prime attribute determining a non-prime attribute?
That is transitive dependency. That is something else. Okay.
No, we call it as partial dependency or not?
Yeah. So again, say, what did you say?
One prime attribute is there, which is part of a candidate key.
Okay.
And then there is one non-prime attribute.
Acha. Okay.
That determines a non-prime attribute.
So no, then it is not a partial dependency.
Okay.
Right? Not. And I will tell you the reason. The reason is when you have done the closure, minimal cover, right? Minimal cover. In minimal cover, you remember while you had, let's say, a dependency of the form, let's say A, B determines some C, D, and you broke it down into two dependencies. So what were the two dependencies?
AB determines C, AB
C and AB determines.
Okay. Can I break it down into something like A determines C and B determines C, like this? No, right? Why? Because the right hand side is something that you can break it down, because all of them are individually repeating later on, depending upon them. The idea is C and D attribute will repeat. This is a definition of functional dependency, right? C and D attribute will repeat on the basis of A and B's repetition. So only when both A and B as a pair repeats, then only C and D individually will repeat. There is a difference between the definition. Only when A and B as a pair repeats, only then C and D individually will repeat. So C and D repeats individually, A and B repeats as a pair. So whatever is there on the left hand side of a functional dependency always works as a pair. You cannot separate them. Okay. You have to consider them together. And therefore, once you have a normal, non-prime attribute on the left hand side, then there is no question of a separate prime non-prime. This whole thing becomes as a whole part, and this whole part is not a part of any candidate key. So basically what I mean is, let's say a candidate key there are two candidate keys in a table, let's say BC and A. Suppose in a table BC and A are the candidate keys. Okay, now you say that I have a functional dependency and the table is, let's say, A, B, C, D, E, suppose. Okay, and you say that I take a prime attribute, so C is a prime attribute.
Yeah.
And I take a non-prime attribute, let's say E.
Yeah, okay. E determines D.
And let's say that determines a non-prime attribute, so let's say D. So C, E, D. So now you cannot separate C from E or E from C according to the definition of functional dependency. CE is always a couple. You cannot break it down because the definition of functional dependency states CE should repeat as a pair and the right hand side can repeat individually. Okay. So since CE can repeat, always must repeat as a pair, you cannot separate it out. So if you cannot separate it out, then you have to check what is partial dependency saying, that the left hand side should not be a prime attribute, and it should, if the left hand side is a prime attribute, then it should not determine anything non-prime on the right hand side. Now then you cannot, since you cannot break it down, you check whether it is a prime, whole thing is a prime attribute or not. No, it is not a prime attribute. right?
Okay.
So C is not a part of any candidate key.
Okay. One more follow-up question. Let's assume there is one more dependency here. C determines E. Will we apply canonical cover and say C determines D is
That's a good question. Okay, so if I in the functional dependency set, whatever it is, some dependencies are there, and then I have C determines C as a part of it, right?
Yeah.
Now the question is, if C, just a second. So if candidate key was C over here, right? So BC together creates, and C.
So candidate key.
Yeah, no,
BC, right?
still it wouldn't make any difference. It will be same. Okay, basically you will not apply any cover or anything, or basically it will still remain the same.
Okay, got it.
Right. Okay, so coming back to our question. So A was the only candidate key. So since A is the only candidate key, there is no other candidate key, and along with that, A is a atomic candidate key. So there is no other attribute associated with A as well. So that means the only prime attribute is A. So since the only prime attribute is also A, therefore there is no question of partial dependency, right? Because I cannot have a part of A, I mean, defining a non-prime attribute. So therefore, no partial dependency.
So example for A, if it is not only single attribute as candidate key, if it like A, B or else A, C, then only we can check the condition of this, right?
Otherwise, prime attribute means what? Prime attribute means a part of a candidate key. So if only one candidate key is there, and that also is a single attribute candidate key, so the only prime attribute is A. So there is no question of part. Part means a subpart, right? A subpart of a candidate key. So there is no question of subpart. So if there is no question of subpart, there is no question of partial dependency.
Right.
We can say that if the candidate key is not the combinations, so it is always true. Right?
Yeah. So that's the point. Basically, no partial dependency is there in R. So that means what? This table is already
into NF.
Into NF.
Sir, I have one doubt, sir. What if two prime attributes are determining one non-prime? At that case, it is partial or not?
Partial.
Okay.
Partial. Right?
Sir, give you example for that.
Same thing. Just consider two partial attribute, which is, let's say, C and BC determining D, or AC determining D. Right? In this example.
Okay.
Yeah. So it is already in 2NF. Now we have to check for if I can move it to third NF. Suppose I want to take it to third NF. And we have already checked its dependencies were preserved, right? So now checking for third NF. How to check that?
Check for transitive dependencies.
Check for transitive dependency. Now what is that thing? The transitive dependency is another dependency where it is saying that any dependency of form X determines Y is transitive dependency when either, let's say not this, let's state it in the negative manner. Any dependency of form X goes to Y is not a transitive dependency.
Either X is a super key or Y is a prime attribute.
Yeah. When either X is a super key or Y is a prime attribute. Either of them, if it is satisfying, any one of them, if it is satisfying, then I will say X determines Y is not a prime transitive dependency. So what is the algorithm? go through all the dependencies of the table, check all the dependency whether are they transitive dependency or not. If it is a transitive, and how to check that? Just check whether they are satisfying either of these two conditions. If one of them is getting satisfied, then that is not a transitive dependency. If neither of them is getting satisfied, then that is a transitive dependency. Right? So we will check that. So in this table, let us check. So candidate key is A. Okay. So prime attribute is only A. Super key is also A. Everything is A. Right. So therefore, A determines BC. What is the left hand side? Right. So X means the left hand side. Why? It's not that X is single attribute. Why? Don't see single or multiple. X means the all the things on the left hand side. Y means all the things on the right hand side. So yeah, so now X is a super key that I have to check. Is X, what is basically in this case, X is basically A. So is left hand side a super key?
Yes,
Yeah,
sir.
correct. So therefore I will not check. So this is not a transitive dependency. Is left hand side a super key in this case? No. So basically C goes to D is the dependency. You can break it up, or let's say if you do not want to break it up, that is also fine, no problem. So C goes to D or C goes to E. In either case, C is not a super key. Is D or E is a prime attribute? No, right?
No, sir. A is prime.
So neither D nor E are prime attributes. So therefore none of these conditions are getting satisfied. Right hand side is not prime attribute. You can, if you get doubt later on, you can also break it down, because functional dependencies can be broken down anytime, right? This is not about cover, minimal cover, anything. Anytime functional dependency is having multiple attributes on right hand side, that is basically two. If I have two attributes, this is basically two functional dependency clubbed together. If I have 5 attributes, that means 5 functional dependency clubbed together. Okay, so that is not about, I mean, I suggested not to do minimal cover or anything like that. It's not about anything like that. Okay, in any case, when there is right hand side multiple attribute, you can simply break it down and treat them as separate functional dependency, no problem. That you can do. So as you can see, CD or CE, neither of them have the left hand side as super key, and neither of them has a right hand side as prime attribute. So therefore, these are transitive dependency. You can consider the whole thing as a transitive dependency as well, no problem. And why is it called transitive dependency? Because you can also see that I have this CD and DE happening together. So it's kind of transitive nature, CD and then DE. So therefore, this is a transitive dependency. So that means there is a transitive dependency in the table, and therefore the table is not in third normal form. The table's highest normal form is 2, which it has already reached. Now I want to decompose it to third normal form. So if that is the question. So how to do that? Whatever is the problematic dependency, and that this algo is same in all normal forms, whether it's 2NF, 3NF, whatever, BCNF, whatever is the problematic dependency, use that to decompose the table. In every case, in case of second normal form, use the, if there is a problematic partial dependency, use that to decompose the table. In case of third normal form, if there is a problematic transitive dependency, use that to decompose the table. In case of BCNF, if there is a dependency which is not a super key, then you use that to decompose the table. But the idea is same. You decompose the table using the problematic dependency. Whichever normal form you are, the logic is same. Now, how to do that? You take the dependency which is the problematic one. In this case, C determines DE. Take the closure set of the left hand side attribute. Basically, you take that dependency and see what are all the attributes that you can derive using that particular dependency. So step.
In this case, both the dependencies C.
I mean, see, it doesn't make any difference, because what did I say? Closure set of the problem causing dependency. This is what you need to find. Isn't it? Problem causing dependencies, closure set. Now, what is the closure set of a dependency? It is always the left hand side. Right? What is the closure set of dependency? If I ask you that A, B determines, suppose GH, all right, and I want to ask you to find the closure set of this dependency. How will you find the closure set of this dependency? You will find AB plus. Now you will see what the original dependency set, and whatever is whatever you can derive using AB plus, that will be in your dependency set. So that will basically AB, GH, so obviously will be there, which is evident from this dependency itself. Other than that also, you'll have to figure out what is there as a closure set of AB plus according to the originally given dependency set in any question. So that all you add all the attributes and this is your closure set. So that means what? If closure set of a dependency means only the left hand side, doesn't make any difference whether I'm taking one at a time, two at a time on the right hand side. It will anyway mean C plus, right? So the idea is you find the closure set of the problem causing dependency, or in other words, you find the closure set of the left hand attribute of the problem causing dependency. Or in case there are multiple left hand attribute, consider them as a group, as a pair. You cannot break it down. I told again, right? So if I had multiple attributes on the left hand side, you would have to consider them as a pair or as a triplet or whatever, how many number of attributes are there. Consider them all together and find how many attributes, basically find the closure set of that whole group. So in this case, the problem causing dependency C determines DE. Left hand side is C. Whatever is on the left hand side of the problem causing dependency, I will find the closure. So C plus. So C, D, E, that's it, right? From this FR, I can only find C, D, E, C, D, this. So yeah, that's it. So this is the closure set. So C, D, and E, right? So now I will use this to decompose the table. I will separate out all these three, keeping C as common between the two tables. So my new decomposed table will be, I will take the left hand side as common, right? Because I'm taking the closure of left hand side, and therefore I will want the left hand side to be common between the two decomposed table, because you can understand, in order to do lossless decomposition, the common attribute should serve as a key on either of the table, or both of the table, or either at least one of the table, it should serve as a key. So since I have found the closure of C, so therefore if I keep C as the common attribute among the table, then I can guarantee that the other decomposed table will have all the attributes being able to be functionally determined by C, because I'm basically doing the decomposition on the basis of closure set of C. So I can always guarantee the other table will have C as the super key, right? So that's why I will take C as the common attribute, or the left hand side as the common attribute. So therefore the table will be A, B, C, and the other table will be C, D, E, R1, R2. So these are the two tables that will be created, and this decomposition will be in third normal form.
So basically you're taking the C, which is A, I mean, it is goes to C2, D, and D2E, so that you're taking the C as an attribute and you're adding into that first and second table. That's it.
Yeah. So just follow this logic, okay? In any decomposition, whether it is 3NF or 2NF. So let me just state this manner, okay? Don't look at it in this. So just follow this kind of an algorithm kind of way. Take closure of left hand side as a whole of the problematic dependency. Okay, problematic dependency can mean transitive dependency, can mean multivalued dependency, can mean partial whatever, right? Okay. Take closure of left hand side as a whole of the problematic dependency. Step 1, bifurcate the table with left hand side Attribute or attributes. If it is a group, there will be multiple attributes.
So bifurcating, it's kind of what is that? Adding it.
Decomposing, dividing. So what did I do over here? All of them were together. A, B, C, D, E. All the attributes were together in the table. I found the closure set of C, C, D, E, and then divided the table into two subtables, R2 and R1.
Okay.
A, B, C, and C, D, E. So I bifurcated the whole R table into two tables, R1 and R2. One with the closure set of the left hand side, and the other one with whatever attributes are left in the original table.
Sir, the C is key for the R2, right?
C is key for the R2. And it will obviously be key for the second subtable, because I am doing the separation on the basis of closure set, right? So it will anyway be key automatically. Closure set means what? It will have all the attributes which is derivable from the left hand side. So if I am taking all the attributes of C and placing them together in a table, that evidently makes C as the key anyways, implicitly, right?
Yes, sir.
So decomposition,
I think it is also in BCNF, right? The previous decomposition what you made.
Yeah.
So ABC, CDE, I think these two are also in BCNF.
No.
In order for that to be in BCNF, I have to check all the functional dependencies serves as super key or not. Right? BCNF's rule is check all the applicable functional dependency, check whether the left hand side is a super key or not. So if I check A determines BC,
yes.
So left hand side is a super key, okay, because ABC will be applicable in this table. So A is a super key, fine. Then I take CD, and CD is applicable over here. So check the left hand side, is it a super key or not?
No.
Okay. Why no?
Yes.
C is a super key, right?
Sir, A only super key, no?
R2 different table, na? These are two tables. R1, A, B, C. R2, okay. C, D, E. I have bifurcated the table into two subtables. That's what decomposition means.
Okay, after decomposition. Okay.
I'm
checking the first, the second row, sir. Second line.
And this whole thing is in 3NF according to my eliminating transitive dependency. Now I will check that whether it is in BCNF as well or not. So in order to check that, I will apply each dependency on the applicable table, just like I check for functional dependency, and then I will check whether that is preserved or not. So in order to do that, I will just check whether, so first is ABC. So ABC is applicable on this one. So let us apply ABC and check whether the left hand side is super key or not. According to BCNF's condition, every dependency should serve as a super key on the left hand side. So ABC is applicable on this one. A determines BC is applicable on R1. So I applied, and now I will check whether the left hand side of A determines BC is a super key. Yeah, it is a super key, fine. Because in this table A determines both B and C. So done. C determines D is applicable on this table. Okay. Now I will check whether C is a super key on this table or not. Yeah, that is also true, because C determines DE. We have done the division on the basis of that. So that is also true. Last is we have D determines E. So we'll check that. We can apply this particular, we will check whether this dependency's left hand side serve as a super key or not. So C D determines E is applicable on this table, right? So I applied it on R2, and now I will check whether the left hand side of D determines C serve as a super key or not. Left hand side of D determines C is D. Is D a super key of R2?
No.
So not in BCNF. How to convert it into BCNF? What is the problematic dependency?
Closure of DE.
Exactly. In this case, the problematic dependency is D determines E. So you take D's closure, same logic. D's closure, which will be what? D and E. Now you break this R2 further into another table, R3, keeping
It's not in 3NF also because transit is this.
Where is it transitive?
C goes to D, D equal to E.
Just I'm coming to that. Just a second. So R3. Suppose. Acha, okay. Let's address that at first. Fine. So you are saying C determines D and D determines E, right? So
Yeah.
is that a transitive dependency or not? Okay. So that is a good observation. Whenever you are breaking a table into one level of decomposition you are doing, you have to again check whether there is leftover any other transitive dependency or not. Okay. So that's a good practice to check that. Always check that. I was kind of in a hurry to go into the next concept, but let us check that now. So is C, D, D, E, are these two pairs of dependency applicable on R2? Are they transitive dependency or not? So is the left hand side super key in case of the first dependency? Yes, because C is a super key of the table D. Okay. In the next case, in the D determines C case, this one, is the left hand side super key? No. Is the right hand side a prime attribute? No, neither of them. Right. So this one basically is a transitive dependency. So this is a transitive dependency. So actually this is also not in 3NF as well. I mean ABC is in 3NF, that is fine, but CDE is not in 3NF. R2 is not in 3NF till now, right? So you have to do one more level of decomposition and that is again same. So DE, you see that here it was not in BCNF because we did not check for transitive dependency once, and therefore it was anyway coming trouble. It was making trouble later on, this DE dependency. Now this DE dependency is anyway becoming transitive dependency, and I will separate it out into another table, and what it will look like is we will break R2 into, let's say, R21 and R22. Okay, the common D will be there, so DE is the closure set of D and CD is basically the other one. So now I have three tables, R1 having A, B, C, and R21 and R22. Now all these three things together, now if you check, they are in BCNF.
Yeah.
Right? Okay. So, so bifurcate the table with the left hand side attribute or attributes in case there are multiple attributes. Keeping the left hand side attribute as common between the two subtables. This is the basic rule for any decomposition that you want to do. Just the problematic dependency changes, whether it is BCNF, 3NF or 2NF on the basis of that. Okay, so that's kind of it, normalization. Okay, fourth normal form, which is basically multivalued dependency. The idea is something like this, that if I have a table, first of all, in order for fourth normal form to happen, there are few rules. First is let us say A, B, C. First is this thing. If there are only two columns, multivalued dependency cannot be there. There should be at least three columns, presence of multivalued dependency. Okay. The second one is two of those three columns should be independent of each other. So these are the two important conditions for MVD to be present, or the chance of the presence of MVD, possibility of presence of MVD in a table, multi-valued dependency. So what does that mean? So I can have a, let's say, a student name field. I can have a subjects taken field, and I can have a sports played. These are the three attributes, suppose. Right now, the student is, let's say, Raj, and he has taken, let's say, physics. Okay, and maybe Raj has also taken chemistry. Okay, and suppose Raj likes playing football, and he also likes boxing. Now you see that in this case there are three columns, that is fine, and these two are kind of independent, right? Because normally speaking, logically speaking, there is no relation between which subject Raj has taken and which sport Raj has played. There is no logical, let's say, correlation between them. But obviously, the sports played and the student's name column are dependent, because which person is playing which sport and which subject is taken by which person. Obviously, they depend on the person, the subject. But so therefore, the last two columns depend on the first column, obviously, according to normal logic. But subjects taken and sports played do not have any interrelation between them. There is no dependency of football with physics or boxing with chemistry, and because of that, while I decompose the table, so let's say I have given you a table with this form of data. I mean, this is the table how it has been given to you. Later on, let us say you break the table due to some, because only these are not the entries in the table, right? There can be multiple other attributes in the table, multiple different rows in the table. The table will be a big table, but there is a snapshot of there is an area of the table which stores this data, right? There can be multiple other attributes. Okay, like this. There can be multiple other datas as well. Now, in order to basically normalize the table, in order to reduce the redundancy of the table, you decompose the table according to the normalization rules. And you are not also worried about fourth normal form MVD. You have not reached to that level. You have, let's say, it was you check the other attributes and everything, and you kind of divide it. I mean, decompose it to the second normal form, suppose, and then third normal form, suppose you decomposed. So while decomposing, let us say you separated the attributes sports played and subject taken, right? I mean, without worrying about multi-valued dependency, you have not yet reached the level of MVD or anything. So you have kind of separated the table, suppose. Now, due to separation of the attributes, later on when you will join the tables, right? When you will join the tables, obviously there would not be any dependency of the form subject taken determines sports played or something like that, or in any case you will not have any interrelation like this. You also will not have any some other attribute which subject taken determines sports played. This also will not be there, because subject taken cannot have any dependency on sports played, either individually or with another group of let's say values, right? So because that is the condition over here, and either way sports played also will have to follow the same rule on subject taken. So if that condition holds, so because you will never have this kind of dependency, because of that, when you do recombination of the table, when you do a join of the table, after you have broken the subject taken and sports played separately, due to that recombination, if you do not have any relation between these two columns, later on you can represent the same data logically with some extra tuples, right? Because since these are not related, I can just exchange these two values. I can say later on when I join the table, I recreate the table at some later point in time. I can have Raj, 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 right? and I can have physics, chemistry, physics, chemistry. I can have football, boxing, right? And boxing, football, right? Because all the possible combinations can form in this fashion. Why? Because joining will take, it will do a Cartesian product. So since if I have a dependency between the last two columns, then this will not happen. Then this can never happen. Because if I have, let's say, a dependency from, let's say this is B and C, if I have a dependency from BC or some form of dependency, some other attributes with that B and C dependency is there, then I cannot have these two things repeating. Both P cannot have F and B when P is repeating, right? Physics is repeating. So that was the reason I said it should be independent. So therefore, in such a scenario, when there is no dependency between these columns, you can have, after joining, you can have these multiple tuples, extra tuples in such a situation. So this is called multivalued dependency. So what is multivalued dependency? Your student name, multivalue determines subject taken, and student name, multivalue determines sports played. So this is called multivalued dependency. Now, how to deal with this? Although this is not, as you can understand, that's not a big problem as such, but then how to basically eliminate this kind of redundancy? Because
the table which you have written below, it has a multi-value dependency between B determines C, na?
Which one? Sorry.
The table which you have written below in the purple color.
No. Multivalue dependency always happens on the first one with the, so it has multivalue dependency of A.
Determines BC, yeah.
Yeah.
Okay.
Right now, you can merge it up and write ABC. That is also fine. Same thing.
So like here, what is exactly the redundancy? I'm not able to see that from data perspective. What is repeating here?
So you can have this 4 rows, right? And there only 2 rows was present. Although the meaning is same, there is no meaning because physics and football, chemistry and boxing, there is no, it's not like that physics has to be there with football. The idea is Raj has to play both football and boxing, and Raj also has taken physics and chemistry. Now, if both these two are in separate columns, because obviously one is subject, another is sports, and both of them are independent, the sports played and the subject taken are independent of each other, but both of them are dependent on Raj. So that means I can combine, strictly speaking, in terms of rows of data, I can say physics associated with football, physics associated with boxing when I do a Cartesian product. Now, you as a person can logically understand it doesn't make any difference, but DBMS is working on relational algebra. It will do a normal Cartesian product and it will think that, okay, there are 2 values for sports and 2 values for subjects. So a Cartesian product will generate 4 combination, 2 into 2. So there are 4 rows getting created. But initially in the first table which I had given to you had only 2 rows, and it was maintaining the full information. There is no loss of information with 2 rows. Right?
Raj physics boxing is missing, right? Like Raj chemistry football, those information is not captured in first table.
Does that make any difference? Raj physics boxing, because Raj is playing boxing and he is taken physics as a subject. And here also, since both the rows are there, if I just tell you from both these rows, you can understand that Raj has taken boxing and football, and Raj is also studying physics and chemistry. It's not like that Raj has taken chemistry in one semester and in that semester only he did boxing. We have not told you anything like that.
That depends upon the dependency provided to us.
Right? That is the reason I told there is no dependency. 2 of those 3 columns should be independent of each other. So these 2 should not have any form of dependency.
Okay, then in the question or any constraint it will be mentioned, right?
Yeah.
Okay.
If it is not mentioned and if they are giving in this fashion, right, they will not ask you this concept. I'm explaining you conceptually what is MBD. Therefore, I'm telling. In the question, they will just mention in this fashion. I mean, just draw these two arrows, which is the sign of MBD, and this essentially means that student name functionally, multi-value determines subject taken. Student name multi-value determine sports played. That means both sports played and subject taken do not have any dependency among themselves.
Oh, okay. And if we have in one question, I remember seeing there is a functional dependency given like subject taken determines sports played along with this.
No,
Will
no,
that be?
that
Oh,
can never happen. That might be something different. Maybe the question was a
okay,
little bit different.
okay,
Okay. Because that violates the condition of MBD, then there is no MBD.
okay, right.
Right? I can have a separate dependency with sports played on a fourth attribute. That is okay. Right?
Yeah.
So I can have something like with all these dependencies, I can have sports played functionally determines, let's say, stadium. And there is a stadium attribute over here. And maybe whenever football is there, I have to follow that. So let's say maybe Eden Gardens is there. Boxing is, let's say, whatever, something. Okay, suppose these are the two stadiums. So when I have this MBD column over here, MBD rows, while I recombine the table later on, then the stadium field of the table will still follow the dependency, and therefore whenever I have football, in both these cases I will have Eden Gardens. So I can have this is that Delhi one. Okay, so I can have functional dependency along with multi-valued dependency, but I cannot have multi-functional dependency among the two table, two rows. Among the two columns which are there in the MBD.
Okay.
Yeah.
And what is the meaning of the word multi determines? Like
Multi determines means this thing, right?
no, like why it is called multi determines? Like
Multi determines means because the same Raj is the column student name is mentioning something about, so it is determining. So obviously you can understand that subject taken is dependent on the student name, right? Because
yeah.
what subject is taken by which student, that is important. So therefore student name determines the subject taken.
Okay.
And at the same time student name also determines the sports played. But then you can say, then I can just mention that student name determines subject taken. Student name determines sports played. You can do that, but then why am I going for a new fancy symbol like this? So this symbol means itself that whenever I have a situation like this, that the left hand side is common, and I'm mentioning it like this, that means that these two does not have any dependency among themselves.
Okay, got it.
This new symbol means basically this thing.
Okay.
And that's why it is multi determines, right? Because as long as you only when you do not have this dependency, functional dependency among sports played and subject taken, that is between the right hand sides, then only you can say that it can be a MBD. Otherwise it is not an MBD, right?
Okay, got it.
Yeah. Okay, so that was the whole concept, but how to basically deal with this thing, and the best way is basically you separate it out into two separate tables with student name and subject taken in one table, student name and sports played in another table, and you whenever you need, so Raj, here also Raj, physics, chemistry, football, boxing. And you don't, whenever you need, you reference these two tables separately in your query. You do not make a join, do not recombine, do not do any of that. So that will make sure that you do not have these spurious tuples coming into play. Right? So that's the solution for that. Now that is in the real world what we do. But now questions that might come from MVD for your quiz or anything. That is basically they will ask you, given a particular table, they might ask you whether this is an MVD or not. Right? For example, let me just. I think the tutorial there are few examples mentioned which were quite nice. There is a complete theoretical understanding of that, but that is basically a formally mentioned the same thing that we have talked about. Let us take just okay. So fine. Let me just make it a little bigger. I think Manideepa has done this video, so you can also check this tutorial if you have any doubt in questions that might come with respect to fourth normal form or multi-value dependency. Please check this tutorial. She has mentioned all the cases. I will just take one example because this video is already there. So, okay. So as you can see on the screen, we have this given table with 4 Java as the course and name Rahul and Arman. Both two names are there, and the books table has this Java beginner and Java advanced as two possible values. Okay. So now the question is asking you identify whether course multi-value determines name is a MVD or not. Right. So given course and MVD, I mean, I'm checking whether name is a course MVD name or course multi-value determines name is a valid MVD or not. So how to basically check that whether a particular MVD is valid or not, or basically it is holding or not. So first of all, you have to check that whether that Java with respect to, so let's say I'm checking for left hand side attribute is course in this case, right? So I will have to check, as the theoretical it is mentioned over here, I will have to check whether all the possible combinations are there or not. So for Java, I have Rahul. For the left hand side, okay, all the possible combination for the left hand side. Since I am talking in terms of course, in this case I am checking the MVD where left hand side of the MVD is course, right? So I will check for, I will talk considering course in, I mean course is the primary tuples or rows that I will see. So course has all the 4 Java mentioned, all 4 cases Java is mentioned. Now I will see that whether in name and corresponding to name, whether in books, whether all the possible combinations with name and books are there corresponding to the course or not. So you see Rahul, course with Java Rahul is associated, and Rahul is associated with Java beginner in the first row, and in the third row again I have Rahul and Java advanced is there corresponding to Rahul. So now I have to see whether the book column, whether the book column, whatever value is present for the book column, is it also there for all the possible values in the name column or not. If Rahul would not have been associated with Java advanced in the third row as it is already there, but suppose it is not there, then I could have said that it is not a valid MVD. Right? And I told you MVD is always with respect to 3 columns. So whenever I am checking for 2 columns, course MVD name, I am automatically implicitly meaning course MVD book also holds. Understand this very properly. Course MVD name, or as the on the screen as you can see, course multi determines name. I also have to check whether course multi determines book implicitly holding or not, whether it is asked or not. If name is holding, book will also hold. Otherwise, none of them will hold. Right? Because as I told, MVD always works with 3 attributes at least. Okay, so the idea is you will check whether all possible combinations are there or not. If it is all possible combinations are there, that means it is a multi-value dependency. Likewise, in my example over here, I drew all the possible combination. 4 rows were there. Why? because there are two different independent values in each column. Football and boxing are two independent value, physics and chemistry are two independent value. So how many possible combinations can be there? 4 rows can be there, right? So as you can see, physics football, physics boxing, chemistry football. So all information is present. So this is an example of a table where multivalue dependency is present, and you need to eliminate that dependency by separating the table. And once you do that, then I can call that this set of table is in fourth normal form, right? Okay, so that is the whole story. But coming back to this example over here, so here I have to just check therefore all the possible combinations are there or not. If one liner you need for checking MVD present or not, just check all possible combinations present or not. So as you can see, name Rahul and Arman is there, book Java beginner and Java advanced is there. So check Rahul is associated with Java beginner, Rahul is also associated with Java advanced. Arman is associated with Java beginner, Arman is also associated with Java advanced, and that's it. Then all the possible combinations are there with respect to Rahul and Java. That's it. So that means this is an MVD, right? There are two here also. There are two possibilities for name, which is Rahul and Arman, and two possibilities for book, which is beginner and advanced. So there are 4 possible rows that can be there for the tuple value of Java in the first attribute, right? For the tuple value of Java in the first attribute, I can have 4 possible rows. So as you can see in this table, 4 possible rows are there, and therefore this is an example of multivalue dependency. That's it, simple thing. Again, I would request all of you to go through this tutorial. I think so. Let's take this one for example. Okay, let's take this particular example. Yeah. So obviously, what Manideepa has done in this, tutorial is how we should formally solve it. What is the way according to the slides we have seen? What are the rules of solving or checking whether MVD is present or not? So that is the way she has explained properly how to formally figure out whether MVD is there or not using these T1, T2, T3 notations and all of that. But if you want to just understand it from the first look, as I already said, MVD means you have all possible combination of different independent values present in different attributes of the table. So just figure that out. If you see this table, right, again the course and name combination is there. So let me compare between course, name and book, let us say. Okay, so you see course, Python, all these are Python. Okay, right? Is this cursor visible? The arrow on the screen, is it visible?
Yes.
Yes.
Okay. Okay. Now you check that Rohan and Ashish are the two values which are associated with this Python. Okay, that is fine. But and over here in the books column, I have beginner, intermediate, and expert as 3 different values. Okay, so that means what? If in the books column I have 3 different values, and in the name column I have only Rohan and Ashish, that is 2 different values. So just for course, just for Python in the course attribute, whenever the course attribute has Python value, right, how many tuples should be there? Because book has 3 different, name has 2 different. So 3 to the 6 possible rows should be there, right? 6 possible combinations should be there. 3 multiplied by 2. So for Rohan, I should have beginner, intermediate, expert. For Ashish as well, I should have beginner, intermediate, expert. So as you can see, I have that. Ashish expert, Ashish intermediate, Ashish beginner, Rohan expert, Rohan intermediate, Rohan beginner. Okay. For addition as well, I can figure that out. 1, 2, 3, 1, 2, 3, no problem. Okay, addition anyway, if it is not asked, you don't have to check because name and book are the first 2 things, that because this course name is what you have been asked to check. Okay. Okay, next is AppDev. So for Python, it is satisfying, right? Python, it is satisfying. Now AppDev. By the way, if you want to ask why I am checking it on the basis of course, why I only considered Python and then I went into checking Rohan and Ashish corresponding to Python. The reason for that is I am checking MVD course multi-determines name is a valid MVD or not. So whenever you are checking MVD, whichever MVD is asked for you to confirm or validate if it is a valid MVD or not, you take the left hand side and consider only that attribute and see what are the possible combinations of the other two columns whenever that particular attribute has the same value. Simple terms, since here course MVD name has to be validated, whether it is a valid MVD or not, you check each value of course when they are repeating. So I will consider all the value of Python as one group and all the value of AppDev as another group. If in case I had some other value, different value, distinct value in course, for example, PDSA, then I would see all the PDSA rows multiple times, whatever many times PDSA is occurring. I will check all those things as a one complete group. So you will check this group wise. Okay, so now I will check for the first is Python group. Because the left hand side is course, I'm repeating 100 times because the left hand side is group course. If the left hand side would have been name, then I would have checked on the basis of grouping on the basis of Rohan, Ashish and Suresh Pratik. There would have been 4 groups then. All Rohan, all Ashish, all Suresh and all Pratik. And inside each of this, inside all the Rohans, I will check whether they are having all combinations for courses, whether they are having all combinations for book, like on the basis of that. So since in this case left hand side is course, I will only check on the basis of one group for distinct values of courses. So now the distinct value of in course is Python and AppDev. So there are only 2 groups. So Python group, AppDev group. Inside Python group, now you check all the other combination is present or not. So inside Python group, I checked Rohan and Ashish in name column only 2 distinct values. In books column 3 distinct values. So if I need to have all the combination between name and books, I need to have 3 into 2, 6 rows. So you can see there are 6 rows. So obviously for Python it is working. Now if you have understood the things that we discussed till now, you can obviously understand that this AppDev it is not working. Why? Because for AppDev I have 2 values in name Suresh and Pratik and 2 distinct values V1 and V2 for book. So accordingly, how many values or rows should I have? 4 rows, right?
Oh, yes, sir.
Yeah. So therefore, I should have ideally I should have other 2 tuples with AppDev and AppDev over here, and Suresh and Pratik over here, with V2 first and V1 after that, right?
Yes, sir.
Yeah. So then it will be done.
So one doubt, like let's consider like AppDev rows are not there. Then this course multi-determines name is true, and can we say it is equivalent to telling course multi-determines book edition?
Book edition means book and edition separately?
No, together. Like course multi-determines book comma edition together.
That means what? If you say that course multi-determines book comma edition together, that makes a little bit.
See course multi-determines name, right? Like we check for all possible combination.
Correct.
The other way also, right? Like let's fix Python beginner 1 and then we can check for both the names to be present.
Like, just a second. For course, what did you fix?
Book and edition together.
No. What were you explaining before that?
Python beginner and 1. Like let's fix that combination and then we can check for the name, right? Like both Rohan and Ashish are present.
Okay. Yeah, fine. If you are checking for book and edition in that case, that is fine. If you are checking for that, okay. Just that whatever is on the left hand side, you have to fix that, and then you have to check whatever is asked for you on the right hand side. No problem.
Yeah. So 2 kind of MVD exists: course multi-determines name or course multi-determines edition of book and edition.
Exactly. Yeah. Right. Okay. By the way, so here therefore it's not. I mean, in this case, since it is not satisfying, it's not an MVD in that sense. You have to add the 2 other values and then you can say it is a multi-value dependency. But so this way you can figure it out very fast. Just check each column, fix the attribute value, fix the row value, check all possible combinations are present or not. If present, you can say it is an MVD. If not, it is not an MVD. But that is essentially you are doing the same thing by using this T1, T2, T3, T4. But that is a more formal way to approach it, and I would request you to watch this video. Just don't apply this short trick. Just see this video, then in the exam if you want you can apply. Essentially you are doing the same thing. This is just the meaning of those formal steps. Okay, so I think we have covered all the topics. Yeah, you want to ask something? You can ask. Otherwise, we will stop. Chalo, fine.
Sir, finally the MVD, what we have discussed. So it must have the combination, all the combination. If it is a one missing, also it is not a the entire attribute. Whatever the condition given is not a MVD. You say right?
No. Yeah, yeah.
And in the lot edition also was MED, and the name and the edition also MED, as it is not changing. Can we say that?
Yeah. That, I mean, I just